that song and let me sing forevermore. You are all I long for, all I worship and adore. In other words, please be true. Fallen leaves drift by the window. The autumn leaves of red and gold.
Recording in progress.
I see your lips, the summer kisses, the sunburned hands I used to hold. Since you went away, the days grow long, and soon I'll hear old winter song. But I miss you most of all, my darling, when autumn leaves start to fall. at me. I'm as helpless as a kitten up a tree. And the moon and let me play among the stars. Let me see what spring is like on Jupiter and Mars. In other words, hold my hand.
Ladies and gentlemen, the event is about to begin in 5 minutes. We would kindly request you to have a seat and join us in the main room. We will have 4 stations lining up for today, and we hope everything will go smoothly beyond the plan. Before we begin, we need you to kindly switch your cell phones to the silent or vibrate mode. Thank you. Assalamualaikum warahmatullahi wabarakatuh. May peace be upon us. Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Good morning, ladies and gentlemen. How are you doing today? Is everything good? It's good to hear that. I hope you had a very good rest and are feeling energized as well. Ladies and gentlemen, it is my privilege to welcome our distinguished speakers and all participants for today's event. We are delighted to host you at the Novotel Bogor Golf Resort and Convention Center for the second day of UN-GGCE International Workshop on the integration of terrestrial, maritime, build, and cadastral domains with the theme Joining Land and Sea. I am Tika from the BIG, and I will be the master of ceremony for today's sessions. Distinguished guests, ladies and gentlemen, proceeding to the next agenda, we are going to have the fifth session, Challenges and Issues. This session will be moderated by Mr. Victor Koo. Mr. Koo is the Director of Survey and Geomatics at the Singapore Land Authority, where he leads initiatives such as establishing national positioning infrastructure, transforming cadastral surveys, and spearheading the Singapore National 3D Mapping Program. On the global stage, he is the co-chair of the UN-GGIM on Land Administration and Management, and serves as Vice President of the UN-GGIM Asia Pacific Regional Committee. Okay, without further ado, I'd like to invite Mr. Koo to take the floor and guide us through this session. Mr. Koo, the floor is yours.
Thank you. Thank you. Good morning. Good morning, everyone. Selamat pagi. Selamat sejahtera. Sampurasun. Something that I learned yesterday, so I hope all of you enjoying the dinner yesterday. We are on the fifth session today. After we heard about the use cases and some technicality on Geoid modeling yesterday. So today we are going to discuss about the challenges and issue in this first session of the second day. My name is Victor Koo. I would like to invite all the four speakers to the stage with me. First up is Daniel Roman. Yeah, please come to the stage. Matthew Basara, and last but not least, Dr. Sugeng Pribadi. Each speaker will have 15 minutes for the presentation. So there'll be 4 presentations. I'll introduce the speaker when it comes to the turn. So, Basara, you want to come to the stage? Thank you. Thank you. So, without delay, I would like to invite the first speaker of this morning, Daniel Roman. Daniel graduated from the Ohio State University with a master's in geodetic science and surveying and a PhD in geological science. Dr. Roman has served for 25 years in NOAA's NOAA National Geodetic Survey, developing Geoid models, serving as Chief for Spatial Reference System Division, then as Chief Geodesist, and now is NOAA's Senior Advisor for Geodesy. So, Daniel, the floor is yours.
Thank you. Appreciate it. So after the bio and looking at the picture, not only do I feel old, I look old, so that's okay. We'll go ahead and get started here, since if we can get the slides loaded. Okay, there. I'll tap dance while we're waiting. I will be speaking to you more broadly about the United States, not just NOAA, but the biggest challenges in joining land and sea for the United States government is the United States government. So sheer number of agencies that we have, as well as the diverse mission and requirements, makes it problematic at times to try to bring them all together. I would say more recently we've now had this separation between the maritime and terrestrial domains. I'll present a little at the end to highlight how that wasn't always the case. But now we've stovepiped into these data collection, modeling, and operation schemes. Remedies to that that I'll go into are the Geospatial Data Act, the Federal Geographic Data Committee, and the US MSDI, particularly the strategic plan associated with it, and adoption of our National Spatial Reference System to achieve the interoperability in accordance with the FAIR principles. So I'll take a moment to brag a little on what we do. We have a number of areas where we are trying to coordinate. We've had more success, I will say, on the terrestrial side than we have had on the maritime side. But the intent of the National Spatial Reference System has been for 200 years to unify all of the geospatial data that we have. With the advent of GNSS technologies, things have kind of drifted, everybody's kind of got into their own lanes and have developed their own pathways for how they conduct their business. Well, my hope is to try and get us all back on the same page. So again, the intent behind doing all that is to integrate all the geographic data or geospatial data sets to make sure that we can get the most out of them, but in the elevation models, where the coastal inundation, where the roads, where the people live, so that you can do a better job at coastal and emergency management, as well as to enable future technologies such as autonomous vehicles and that may need higher precision and accuracy in terms of their navigation systems. So then, what groups do we have here? So I tried to group the more maritime ones on the blue side and the terrestrial on the green side. But these are by no means all of the agencies that are engaged, but I'm only highlighting a few that are of interest here. On the maritime side, you've got the U.S. Coast Guard, whose job is to maintain aids to navigation, as well as some law enforcement activities. But the Army Corps of Engineers, who, although a part of the Department of Defense, has a lot of civil responsibilities in the maintenance of levees, dredging of the channels. And finally, within the National Ocean Service, the service with which the National Geodetic Survey is located, I have a number of sister offices. The Office of Coast Survey being the primary one, which engages with IHO and does all the charting. I would note that that is a group that they're trying to find a way forward to try and meld a lot of the responsibilities and charting within the National Spatial Reference System, but also within WGS-84, and there's some issues with that. Coordination comes under the Committee for Maritime Transportation Systems, and particularly the Trident meetings that are assembled, the three that I've just laid out. And I can tell you last week that they all met, and they proudly announced that the solution to all of this was to position the build infrastructure with WGS-84. And despite my admonitions against doing so, they decided that that was their solution because IHO says that it's okay to use that, and that's where I come to this meeting to try and lay out the case for why those standards aren't necessarily incorporating some of the aspects that we need. And I will remind people that the WGS-84 system is developed by NGA. It is intended to position where you are, where your target may be, and how to navigate to it. It is not necessarily suited for a lot of the terrestrial things that I'll get into here in a little bit. On the terrestrial side, they kind of had NASA at the top because they do both marine and terrestrial. They do a lot of the ocean modeling, but they also work with us in vertical land motion, USGS, DEMs, and river gauging, but they also deal a lot with coastal inundation. And again, a lot of the terrestrial side is already using the current National Spatial Reference System within the U.S. And coordination is through the 3D Elevation Federal Interagency Coordinating Committee, 3D-FIC, because we love acronyms. I think everybody does. But our coordinate system is based on the International Terrestrial Reference System, and we adapt it to the USM specific for the National Spatial Reference System. And standards that we typically are using are going to be ISO and OGC oriented. All right. So then, how to bring it all together? The Geospatial Data Act of 2018, signed by President Trump, actually states that the Federal Geographic Data Committee, which existed before this, actually has primary authority. The problem in the U.S. is there is no central geospatial authority. We have a committee, an interagency committee, and that's what the FGDC is. The difficulty is that the FGDC never really had anything. They maybe get presidential directives. They never had formal authority. So they really didn't have the authority to tell any of the agencies what to do. Geospatial Data Act changed that. They codified all the rules and requirements. They put the FGDC in place. A lot of the terminology that you see in it came from a lot of the language you see in the UN, in terms of like the UN-GGIM and its associated resolutions, as well as the GGRF. But more specifically, they're dealing with telling all the other agencies you have to abide by what we tell you to do, because we're going to develop standards that once codified, you have 5 years to demonstrate you're in compliance with, or you start to lose funding. That's called the hammer. So that's one way certainly to get the attention of a number of agencies, and we have seen a lot of action now from a lot of these agencies that are interested in trying to align their activities to the National Spatial Reference System. So within the FGDC, they developed the most recent National NSDI Strategic Plan for 2025 to 2035, highlighted in blue. Not sure anybody can read it in here, but it does state that basically that U.S. geospatial data should be aligned to the National Spatial Reference System. So it is codified both in the GDA empowering the FGDC and now at a national level, a strategic plan that says align all of your data to this system. So to that end, then, we have a Federal Geodetic Controls Subcommittee. The task of the FGCS is to try and coordinate across the government to make sure that the movement towards the NSRS is reasonable, that we provide the tools, we help other agencies move towards this unification that we're seeking. Key to keep in mind here is that the NSRS will be accessed via GNSS, not just GS84, not just GPS, but all of the NSRS, and that we will use a geoid height model calibrated against reality to determine the physical heights. And we'll provide the data and tools to support this. So we have to develop all this, and we're spending probably the next 2 years, the dog and pony show, as we say in the US, going from one place to another, trying to show these agencies why they need to do it, how they need to do it, and what they're going to need to do for their next steps. So for reference, so to speak, the reference frames themselves that we have span roughly half the planet, the Pacific being the biggest one, with a lot of overlap with a number of the nations that are present here. So we have, indeed, a great incentive to interact with your countries to make sure that what we're devising isn't completely just US-centric, but that it melds well with what everybody else will be using in the area. I would note that these reference frames are based on ITRF 2020. So, as with many of you, we have customers that don't like coordinates changing. So we apply an Euler pole to take out the bulk rotation. Okay, that's basically the difference. And then we also map the deformation that might be occurring within those frames to monitor any change that might be happening locally. But these are the 4 principal frames that we'll be working towards, and within those frames then we will devise a geoid model to determine the physical heights. Now the geoid model on the right should be coming up on our beta website for test and evaluations, if not this week, in the next couple of weeks. It spans a quarter of the Earth. It basically provides the unification from Hawaii to Alaska through most of the parts of the United States, with the exception of Guam and the Commonwealth and Northern Mariana Islands and American Samoa. They were just too far out for us to try and incorporate into the model, where we're using similar techniques for those regions. And I'll get into it in a bit, but we're going to look to particularly Micronesia and some other places. Our gravity mission did complete, but we still have the capability of continuing to do collections. We're doing so right now in the in the Canadian areas at the behest of the NGA, but there are other areas, particularly in Micronesia and other places, where NOAA has an interest because they do charting and such to support those nations. And such, there may be an interest in supporting airborne gravity efforts to try and develop a geoid model in those areas. There's a lot of hypotheticals in there, though, so don't hang your hat on anything. The final thing I'll note is that the geoid model we picked, the datum that we picked, was based on comparisons at 200 tide stations scattered around the US and Canada. Key there is there is a significant topography of the sea surface. You're talking meter level variations due to the Gulf Stream and things of that nature. So we used a priori models to try and remove those. And at the tide stations, then we calculated the geopotential numbers. And what we found is pretty decent agreement. The Gulf Coast, the model was maybe a little off, but what we found is pretty much agreement that's in around the equivalent of about 10 centimeter range, plus minus 10 centimeter. What that did, though, is it highlighted, I can't use the laser pointer, but at the bottom, the value that we adopted for the W0, which happens to be the one the IAU selected for the Earth, rather than the one that the IAG has put forward. I can transform between them, but the point here is I can point to my customers to a tide station and say, I use that tide station to determine heights along the shore, on land, and at sea. And that's something your customers may have a liking to, something that maybe they can understand more readily than, say, we tracked satellite altimeter data sets and we came up with a mean value and converted it. I mean, scientifically, that might make more sense, but for the a layperson, it's going to be much more useful to point to a tide gauge. So let's bring that into, you've seen this cartoon a couple of times now, I'm sure, but the same ideas. So there's a mean sea surface, there's the tide gauge. The difference between the geoid that we picked and that tide gauge is the topography of the sea surface. But you also have satellite altimeter data scanning alongside that gives you the mean sea surface extended out. And I didn't mention it, but one of the other divisions within the NGS is the remote sensing division. One of the tasks that we have is to fly the shoreline. So we fly the shoreline, usually at mean low water, and we look for all of the different breaks so that we know where the different tide zones are. And it's a topobathy LiDAR, so we see onshore and offshore, out to maybe 10-meter resolution, depending on the clarity of the water. But the idea is that with the shoreline data, the shoreline mapping, and the charting from the Office of Coast Survey and the USGS DEM models, we're able to integrate the bare earth model underneath the ocean as well as in the air and make it all one seamless border. And then we can take this information and we can integrate that into our V-data model. So a lot of the work that the Office of Coast Survey does is on a sort of reference tidal data. So they basically use GNSS to figure out where they're located. And then they use tools like V-Datum to convert into the various tidal datums as well as to relate to what's happening on land. So what this does then, it produces a mechanism by which we can integrate all of this data and we can provide it as a tool for access for people who need to move between the different types, from the tidal datums to the orthometric datums to the geometric datums. And one of the tools that we have, I don't show it here, but we have a tool called NCAT, which is coordinate conversion tool. The back end of NCAT and V-Datum will produce identical results in the terrestrial regions. The addition on V-Datum is that you also have the different tidal datums. So final slides here. I will point out that I mentioned at the outset, historically, we've been doing this for a while. 1807, the Survey of the Coast was established. The intent was, no offense to my British colleagues, but when they left with all the Admiralty charts, we had to figure out what the ports were so we can get shipping in safely in and out. So to that end, they implemented the Survey of the Coast. Well, before they could actually throw a lead line over the side, you first had to put in aids to navigation. And before you could put those in, you had to have geodetic control to position the aids to navigation to position the ships. Then you could throw a lead line over the side. So all along, we've been established through about 1970 when NOAA was established. They just established the Coast and Geodetic Survey, and now we're embedded inside of the NOAA as the Office of Coast Survey and the National Geodetic Survey. So we still exist, but we've morphed into inside NOAA. So I believe I'll leave you with that, other than to point out these are the core stations that we have. That we work with APRA in particular to try and make sure that we're coordinating our data sets, but these are the access points by which we then provide access to those 4 frames that I showed earlier. Thank you for your attention.
Thank you, Dan. You may take your seat. Thank you for sharing with us the landscape of the agencies in United States, the different coordination organization, as well as the different reference frame that has been used in United States. So the second speaker for this session is Matthew Ellis. Matthew is an experienced professional in marine geoscience, currently serving as the Assistant Director for the Marine Resources at Geoscience Australia. In this role, he leads the Marine Resource Initiative, which fosters collaboration in marine geoscience between Australia and Southeast Asia. Matt has a strong background in Earth observation science, geographic surveying, and nautical cartography, having worked in both Geoscience Australia and the Australian Hydrographic Office. So Matt, today you are going to share with us how Australia overcome challenges to create seamless national scale topography surface. Yeah. So the floor is yours, Matt.
Salamat pagi, terima kasih telah mengundang saya ke Bogor yang indah. Good morning, everyone. My name is Matt Ellis, and I'm thrilled to be speaking today about Geoscience Australia AusBathy Topo Grids. Particularly, I'm going to be focusing on the challenges that Geoscience Australia overcame in creating a seamless national-scale bathy topo surface. I'd like to start by thanking the UN-GGCE and BIG for hosting this event, as well as my colleagues at Geoscience Australia, Rob Beeman from James Cook University, the University of Sydney, and the Australian Hydrographic Office for their contributions towards the creation of the AusBathy Topo Grids. So I might start the speak sort of reflecting on what we were talking about yesterday, and I think a lot of the conversation was around the increases in geodetic precision that were required to achieve certain use cases. This talk's sort of going to flip that question on its head and say, what happens if you accept that you don't have the available data for a geodetically controlled surface? What can you still achieve with that? And I come from a team that really works on marine spatial planning in Australia's Maritime Boundaries program. So we sort of see these three clear reasons why Australia needs a seamless bathy topo surface. Firstly, Australians overwhelmingly live in coastal communities. Secondly, the activities on land in these coastal communities impact our oceans. And thirdly, integrated jurisdiction management requires knowledge of the land-sea interface. So, what are Geoscience Australia's AusBathy Topo Grids? Published in 2023, the AusBathy Topo Grid is a 250-metre resolution, national-scale elevation and depth model for Australia. The AusBathy Topo 2023 grid replaces the Australian Bathymetry and Topography Grid, which was published in June 2009, so quite a gap between editions there. Geoscience Australia can now produce a seamless elevation model that, while it does not have geodetic precision, meets requirements for many integrated management and scientific applications, and will also be releasing an improved version early 2025. The 2023 grid provides a seamless 3D surface with improved coastline definition and greater clarity of the transition between land and sea that can be used to inform planning and management decisions at regional and national scales. These improvements are due to the incorporation of Earth observation data. The AusBathy Topo grids are the best achievable surfaces using available data. In constructing these grids, Geoscience Australia focused on morphological integrity over geodetic precision. They are suitable for applications that require accurate shape, not accurate depths or heights. To cover my backside a bit here, these surfaces are not for navigation and not for local scale analysis, but were developed for regional and national scale scientific jurisdiction management applications. Alongside the national 250-metre grid, Geoscience Australia is also iteratively producing regional scale joint AusBathy topo surfaces, focusing first on areas that support the Australian government's requirements. And I think that's something that is a really good point to take out of this talk. These grids are really created to address government needs. They weren't created for the sake of having a grid. Under the Australian government's Resourcing Australia's Prosperity Initiative, Geoscience Australia plans to release these regional products around Australia's coastline at 30-metre resolution in coastal waters and 100-metre resolution in deep water. On the screen on the right there, you can see our grid for the Bass Strait at 30 metres, which is a really important region in Australia for the development of our offshore wind industry. So a really good example of how these grids are addressing government needs. So you might be asking right now, Matt, what can you use a grid for if it doesn't have precise geodetic control? And the answer to that is really any application that values surface shape more than geodetic integrity. So some of these use cases that we've used the grid for are maritime jurisdiction management, unclossed baseline delineation, especially with respect to capturing the shape of the reefs in the Great Barrier Reef and Torres Strait, geomorphological classification, blue economy industry development, including the offshore wind establishment, hazard and tsunami risk modelling, coastal zone management, and climate vulnerability assessments. What these grids aren't suitable for are for applications that require the geodetic integrity. We're all sort of here this week trying to achieve things like sea level rise monitoring and flood mapping. This is not the surface for those use cases, but there are plenty of other things that we can use it for right now. So today I'm going to present on the 3 most significant challenges we faced in the production of the 2023 AusBathy Topo Grid and how we overcame these challenges. The first of which is acquiring data on a national scale to ensure effective coastline control. The second is removing the datum step between land and sea. And the third is integrating data from multiple sensors, datums and varying levels of quality. I'd also just like to note that Geoscience Australia is actively developing geodetic solutions to some of these challenges, such as the AusHydroid model. In the meantime, we can still produce a surface for applications with low precision requirements through manual interventions. So, challenge 1, acquiring data on a national scale to ensure effective coastline control. The 2023 publication of the 250-metre grid superseded the 2009 grid. This older grid was a great product, however the absence of data covering the shallow water and coastal zones in many parts of Australia resulted in poor coastline control. So here's the 2009 grid on the screen, and if we zoom in, we can see that some areas of the grid have very poor coastline control. Noting that many of the applications of a national elevation model are dependent on coastline control, improvements to the coastal zone were required. We can also see the lack of data density in the shallow water zone has resulted in significant interpolation, which is not a suitable representation of the seafloor. The challenge Australia faced was with a jurisdiction as large and in some cases remote as ours, mobilising expensive sensors such as bathy LiDAR on a national scale was not feasible. Fast forward to 2023, and I want to highlight the significant improvement in coastline control and grid fidelity we can see in the 250-metre AusBathy Topo Grid covering a remote part of Australia's northwestern coastline. We can observe the impressive coastline control these new grids have achieved, as well as significant improvements to the shape of the seafloor in the shallow water zone. These improvements were made possible by the inclusion of innovative Earth observation techniques to fill in the gaps where high-quality bathy LiDAR was not available. There are 2 key Earth observation technology advances that I'm referring to when I explain why the 2023 grid is such a significant improvement over our 2009 product. The Digital Earth Australia program at Geoscience Australia has produced an innovative methodology to capture elevation in the intertidal zone by combining satellite imagery and tidal models. The intertidal elevation product provides a cost-effective mechanism to produce intertidal elevation on a potentially global scale. So that's the animation you can see on the left there by my very talented colleague Robbie. And you can see how we have annual updates to this intertidal elevation model. Similarly, Geoscience Australia has long supported the development of satellite-derived bathymetry as a portable, cost-effective method of producing bathymetry over the shallow water zone in the absence of bathy LiDAR coverage. By including these Earth observation datasets, it is possible to produce a high-quality elevation model that joins land and sea together in a manner that has not been possible previously in the Australian context, as well as many other coastal states in the Indo-Pacific. I might just take a drink. Moving on to the second challenge, which is removing the datum step between land and sea. Geoscience Australia has recently completed an analysis of our maritime jurisdiction and calculated that only 35.2% of our seabed has been mapped in sufficient detail for the production of regional scale AusBathy Topo grids. Considering this, we cannot limit ourselves to only data that fits the surface after geodetic control is applied. While national surveying efforts continue, Geoscience Australia utilises the best available data to build our grids facilitated with manual interventions. I've previously highlighted that the AusBathy Topo grids prioritise seafloor shape and morphological integrity over absolute accuracy. Even when performing geodetic transformations to normalise all source data to a mean sea level tidal datum, we still encounter datum shifts. To preserve the morphological integrity of the grids, we perform manual interventions in the form of vertical shifts to ensure that seafloor shape is preserved and the grid is free of artefacts. The goal we have with removing this datum step is to produce the best morphological surface with available data, free of artefacts, suitable for applications that value morphological integrity. A repair and replace method is used, where the impact of new data is assessed on the existing grid. Manual interventions are taken when new datasets produce artefacts and shifts. These manual interventions are as follows. Firstly, elevation data is the vertical basis for the grid. The previous grid is used as the base skeleton in which new data will be incorporated. Bathymetric data is shifted to match elevation data when datum steps are encountered at the land-sea interface. Expert knowledge of hydrographic surveying is used to guide manual interventions resolving conflicting bathymetry of similar quality, and bathymetry that threatens the morphological integrity of the grid is not included. The final challenge I want to talk about is how we overcame producing a seamless grid using data from a very, very broad range of sensors. You can see on the screen some, but not all, of the different types of elevation and bathymetric data used. All these types of bathymetry have different pros and cons. For example, E&C soundings provide a national scale data set of high quality depth on a single tidal datum, but also result in pimpling in deep waters due to a shoal bias. Considering this, not all source bathymetry is created equally. We therefore undertook a fill-in-the-gaps approach, integrating all data into the single surface. The fill-in-the-gaps approach means that if an area is adequately surveyed using a high-quality sensor, we do not attempt to additionally incorporate lower-quality data for that area. Essentially, we have a set of rules which guide some of the types of bathymetry being incorporated into the grid. So SRTM elevation was firstly trimmed using Geoscience Australia produced low water coastlines and then put precedence over all other data. Multi-beam and bathy LiDAR were then our overruling bathymetry data sets, and it is rare that they overlap. E&C soundings and other high-quality bathymetry, such as single-beam data, are the next rung down from multi-beam and bathy LiDAR, and then we look at EO data sets, such as DE intertidal and SDB to fill in the remaining gaps. When conflicts arise between bathymetry sources that are comparable, they are assessed in a 3D point cloud editing software such as Chimera against each other and the base grid to identify if one of the datasets should be removed or shifted before incorporating. Before I wrap up, I'd like to highlight one of the ways that Geoscience Australia is using the regional AusBathy topo surfaces. My colleague Rachel Nansen has developed a two-part classification scheme using regional ABT services to map morphology and geomorphology. This classification transforms the AusBathy topo grids into decision-ready information for applications such as the establishment of a deep water representative marine park network, the establishment of Australia's offshore wind industry, the suitability of the seafloor for activities such as cable laying and more. This is a great application of the AusBathy topo grids because it is an application that values seafloor shape more so than absolute depth. In summary, Geoscience Australia's contribution to the development of innovative Earth observation techniques to capture elevation in the intertidal and shallow water zones has resulted in dramatic improvements to the quality of our joint land and sea grid. These techniques present a cost-effective mechanism for states who, like Australia, are unable to capture their entire jurisdiction with high-quality, high-cost surveying techniques, a path forward in the production of a seamless land and sea elevation surface. Standardising the production of national grids on a global scale would offer significant progress on the pathway towards sustainable development goals covering marine conservation and blue economy development. Jaramakasi, thank you very much.
Thank you, Matthew, for sharing with us the work in Geoscience Australia. This is really a classic example of joining sea and land, looking at multiple sources of data, using the different types of, the different datum, different resolution of data. What make my curiosity is why Bathy topo and not topo Bathy? just to put some controversy to the discussion. Thank you for that. Yeah. So next speaker, I'll leave the question and answer to the end. I think we will invite next speaker, Basara, from GSI. Basara currently is a director for Geospace Geodesy Research Division, Geography and Cluster Dynamics Research Center, GSI, Japan. Basara in international communities has chaired the working group 2 for the Geodetic reference frame in the UN-GGIM Asia Pacific. So today, Basara is going to share with us on how Japan could join land and sea data. The floor is yours.
Thank you, and thank you, Victor. Good morning, everyone. First of all, I would like to appreciate GGCE for giving me this opportunity, and also appreciate the host, BIG, for hosting this wonderful workshop. So my presentation is a joint presentation by GSI of Japan, which is responsible for reference frame inland in Japan, and also the Hydrographic and Oceanographic Department, Japan Coast Guard, who is responsible for reference frame in ocean. So before moving to my presentation, I'd like to share some findings from annual session of Geodetic Working Group of UN-GGIM EP, which was held in India last week. One of the big findings from our annual session is there are strong needs from member countries for capacity development in modernization of height system. There are the most of the countries already using GNSS cores, but there are still challenges in how to use Geoid for their national height system and implement it to the practical use of the Geoid. So today's my talk is related to the challenge of the regions, the countries in the region somehow. And this is the topic of my talk. The approach now we have in Japan to integrate land and sea is very almost the same or very similar to the approaches by the other countries. But I'd like to share the current situation in Japan, including ongoing and future works, and also the challenges in Japan. So first, current height system in Japan, inland. Our current height system is maintained by first order leveling, which has 14,000 kilometers long, within 170,000 benchmarks. And we are conducting the repeated geodetic leveling campaign since 1918. And each campaign we took now 10 to 15 years. But you know, it takes the geodetic leveling takes long time and also very costly. So it is very difficult for us to continue geodetic leveling to maintain our geodetic leveling network. And our height system, the data origin is in mean sea level in Tokyo Bay. We conducting tidal gauge observations since 1894 and monitoring the sea level with this tidal gauge station. The current our height system refer only single station in Tokyo Bay. And now we already are using Geoid model for the height determination by GNSS observation. Our current height Geoid model is hybrid Geoid model. We developed a gravity Geoid model and fitted to the GNSS level Geoid height by least square collocation. And this hybrid Geoid model is fully consistent with the oscillator height of the first order benchmarks. And we are now considering to update the height system in land in Japan. We are now developing new gravity geoid model of Japan, Geoid 2024. We also completed to establish the new gravity geoid model. And accuracy, compared with the GNSS leveling, the accuracy is about 2.5 centimeter. And we conducted nationwide urban gravimetry, and we also use land gravity data, shipborne gravity data, satellite gravity data, and also altimeter gravity data to construct new geoid model. And you can see the airborne gravity measurement flight lines on the middle figure. We spent 5 years to cover the whole land with gravity, airborne gravity. And with this new gravity geoid model, we are planning to introduce new survey rule to Japan, which we call GNSS height survey. In this survey, we use a new gravity geoid model as a reference frame surface and allow all users to use this gravity geoid model to determine orthometric height with GNSS survey. And the users of the geodetic leveling, we allow users to conduct the geodetic leveling survey from all GNSS core site to determine the orthometric height of benchmarks. And you can see the difference between the new height and the conventional height. As I mentioned, we developed the gravity geoid model, and the original gravity geoid model is consistent to the W0 geopotential value of global geodesy, global sea level, which is recommended by the IAG. And shifted it to fit the mean sea level of Tokyo Bay. Local sea level is still very important for social applications, so we decided to shift our new gravity model to fit to the local sea level. And change of the height values caused by the nationwide update is up to minus 30 centimeters. This change might affect some local users, but we are now doing a conversation with users in our height system, local government, central government, and private companies. And also we are planning to provide a guideline how to practically adapt these changes to the almost all social applications. So let's move on to the marine part. Same as the other countries, hydrographic survey covering all ports in Japan is providing the chart datum for all ports in Japan. And chart datum is determined by hydrographic survey from land benchmarks and tidal observation. But now, we are now considering to modernize height system in Japan by introducing episodal reference survey, which can determine the chart datum from episodal height of water surface and chart datum model, which is constructed from geoid model and also dynamic ocean topography determined by the observation of sea surface along the coastline of Japan. Also, sea level, tidal change determined by the already existing the list of chart data and the construct chart data model. Our colleague from IHO will explain details about this concept in his presentation later today, so I do not go into details, but the concept is almost same as the ones with other countries. So, let me go into the challenges on height system in Japan. The first, in our new updated height system in Japan, all heights are connected to geoid and elliptical side in both land and sea, so it will be consistent at especially at the time of update. But we have a huge cluster deformation, and this means that this cluster deformation causes a change in sea level along Japanese coast. You can see one example of the cluster deformation, accumulated cluster deformation along the coast of Japan, especially after the area of the Tohoku earthquake. A huge earthquake happened in 2011. You can see co-seismic displacement along coast 1.1 meter subsidence. But co-seismic displacement is relatively easy. We can just update the height in the area of affected by earthquake after. But co-seismic deformation causes an uplift and after the earthquake, and this uplift up to 80 centimeter in 13 years and still continuing. So we need to handle this continuous change in vertical components along coasts. And also, we can connect land and sea along coasts of Japan using tidal gauge observation. But the challenge is how we should handle the dynamic ocean topography, especially caused by the strong currents along in the Pacific Ocean. This figure shows a difference between the geoid and the sea level surface caused by the Kuroshio current, strong ocean current. The difference between the geoid and the sea surface is up to over 1 meter in the area of the strong currents. So we need to handle this, but we are still struggling to find a solution. So we are now considering to update our national height system in land, and also we are now considering to adopt new survey method in marine area to refer the same reference surface, geoid and reference ellipsoid, from both side, land and sea. It will make us be able to make it clear the relationship between land and marine sea along coast of Japan. The challenges are the time variation in the reference frame. We need to handle the time variation. And also, sea level rise is increasing, and dynamic ocean topography around Japan is also a challenge. We need to handle this complicated variation in spatial and also time, both. And the possible solution for these challenges in land. The simple solution is just adopt dynamic height reference frame. Technically, it is already possible, but the challenge is how to persuade people to adopt dynamic frame, because the most users do not comfortable with the change of positions of their lands. Also, we need more time to make understand the people the value of dynamic frame. And another challenge is in marine regarding how to handle the dynamics of ocean topography, and also how to handle the change of the sea level along coast. So we need to continue our routine observation at the ports and tidal stations to track the change in ocean. So this is final slide of my presentation. So thank you very much.
Thank you, Basara-san. You may take your seat. Yeah, you have shared with us very complex activities in Japan in height and geoid modeling, both on land and in sea. And also, I think the interesting thing is about how to manage the changes for the local people. That is a very difficult task to convince the people to use the new datum. Yeah. So we are actually well ahead of time. I think the last speakers of this session is Dr. Sugain Pribadi. He's a professional in the field of geology, tsunami studies, and seismology, currently working at BMKG, which is the Meteorological, Climatological, and Geophysical Agency in Indonesia. He has an extensive academic background, including a PhD in seismology from ITB, as well as a master's degree in the tsunami from GRIPS, Japan. His research has focused on tsunami simulation, earthquake characteristics, and the seismic activity of tsunami generating earthquake. Yeah. So I'll give the floor to Dr. Sugain for his presentation on the title of Challenges and Issue in Developing Tsunami Model, a Case Study in Indonesia. Yeah, the floor is yours.
Distinguished ladies and gentlemen, especially the chairman of PIG, UN-GGCE, and everybody, good morning, selamat pagi, and assalamualaikum warahmatullahi wabarakatuh. Thank you for inviting me to attend this workshop. I'm very happy because during today's I have many new knowledge here from many scientists, and happy, very happy. Okay, my title is The Challenges and Issue in Developing Tsunami Model in Indonesia. I work in BMKG, Jakarta. My outlines is, I want to talk about background, tectonovolcanic disaster in Indonesia, the task of producing tsunami maps, the needs of high-resolution data, the use of tide corrections, existing conditions and challenges, and summary and recommendation. First of all, I want to talk that Indonesia is a supermarket disasters. Yeah, many disasters in Indonesia. There is a flood, drought, landslide, volcanic, earthquake, and also tsunami. The largest one is the flood, yeah, 20%. The tectonovolcanic only 2%, but when they occur, they're causing large loss of life and material. The rough statistically calculation show the recurrence of big earthquake only 3 years, once per 3 years, and destructive tsunami 5 years. Yeah. This is rough statistically. And this is the map distribution of epicenter in Indonesia from NOAA. Thank you, NOAA, giving us the data. It's 287 events for magnitude more than 5. And tsunami, 91 events from 1711. And the volcanic from before century, minus 4,000. We have 291 mountains and 52 tsunami caused by volcanic. And the potential volcanic tsunami, there is 13 volcano. I get the source from the magma SDM, which is a very potential volcanoes in Indonesia recently. Some of them already come to the location and make some small simulation. And we know the tsunami is very familiar, it's from Japan, Professor Kenji Satake. It is derived from geological process, can be earthquake, volcanic, landslide, and it made the propagation and then come to the coastal, can map the waterhead, current damage. And in my opinion, in my thesis and dissertation, that you can make the characterization of tsunami in Indonesia. We have 5. That tsunami genetic for far field, near field. Tsunami earthquake is medium magnitude but can cause high tsunami. And non-seismic tsunami like Palu 2008 and Krakatau 2008 is a very strange tsunami. Yeah, we are surprised at the time. Yeah, because very local, but make high tsunami and make big damage. Yeah, because of tsunami and the liquefaction. Yeah. And the last one is meteor tsunami. It's now it's very popular, yeah, since the Hungatunga 2022. Indonesia, since Palu 2018, and Krakatau in same time, same years, 2018. So then we have make some progress. At the time, we use the TOS model in our in BMKG operational, and after that we make some work progress from 2021 until 2004. We find the models, the Comcode tsunami. We make some digitization, interpolation, counter, and I've ever studied from the BIG guys, Mr. Teguh Sulistyan. I don't know if he come here or not. She taught me about how to make the integration data, BATNAS and DEMNAS, and thank you. And then we make some, next year, we make some confirmation, make evacuation maps and shelter from the tsunami maps. And 2023, we make some multi-layer integrating the BATNAS and DEMNAS. And this year, my team make some field data. We make a field survey using GPS Geodetic, LiDAR, UFV, in some collaboration with Brins College, with only small region in Bengkayang, Kalimantan, Sulawesi, Ambon. Yeah. And maybe 2025, we make scale up. We buy some HPC, high performance computer, with GPU, and we will make some system processing of Merah Putih from Indonesian people. And at the time, we want to parallel to the operational model from within TOAS. BMKG operate the tsunami early warning as 24 operational hours per 7 days. So when earthquake detection, at that time we have the TOAS model within 2 applications, Tsunami and EC Wave, giving the model. Yeah, this is the difference between EC Wave and Tsunami. The EC Wave is the on-fly simulation, and this is our task as the RTSP, Regional Tsunami Service Provider. We have serviced the tsunami warning from all Southeast Asian and Indian Ocean countries, and we use the finite difference and linear long wave. And tsunami, we create the database 22,000 scenario of tsunami, but we use the finite element and triangular mesh inundation and extreme data. This is the tsunami processing for Indian Ocean. We create 22,000 scenario in all segment. Sorry, it's not clear, yeah. But we use the segment from PUSGEN. Yeah, PUSGEN is the center of. This is all scientists from earthquake, geology, and also tsunami in Indonesia. They cooperate, make some segmentation of the earthquake, whole Indonesia region. So BMKG, we make the source of the earthquake from PUSGEN. So the result is 22,000 scenario, and this is the finite element triangular ridge. Yeah. This triangular ridge, the red one for 500 meters, the yellow is for 500 meters, and the blue ones for 50 meters. Okay, the task of tsunami maps is for to produce the evacuation map and confirmation center. We cooperate to BNPB, and we make the renewable tsunami maps because BNPB made some old map, yeah, and it's 10 years ago. So we try to make the new ones, and we make some training to the citizens for local people how to evacuate themselves. Our waves also for the guidance for the stakeholders of disaster, the UNESCO help us to how to make assessment of tsunami hazard map, to prepare for evacuation procedure and tsunami emergency response. So after that they certified some villages can fulfill all the requirement and preparedness training. There's a dozen villages in Indonesia. There's Bali and Benua, yeah, Bali, Benua, and Samar, Sumatra, and NTB, Nusa Tenggara. Okay. And this is the need of high resolution data. For this one, we use Comcode model. This is the models given by the Xiaoming Wang and Howard. And Aditya Guzman from GNSS New Zealand. And we use leapfrog finite difference cam. It can be used for operational condition and also for scientific evaluation because can give the high resolution. And the source can be used for the earthquake, volcanic activity, and landslide. Yeah. This is the flowchart how to make from the input and the output data. And it's the numerical one. I don't want to explain this. Is very mathematically. And you use for some scientific journal. Yeah, the source in the Philippines, the Manila Trends. There is the journal that if Manila make some accumulate segment, yeah, it can be made it up 9.1 and can be affected to all countries in Southeast China Sea. Also for Bengkayang or for Pantai Gosong. The Pantai Gosong is the prospective site for the power plant in West Kalimantan. Yeah, we also have the more detail with UFV data and field survey. And later on, next year, we want to make some simulation for the Sarawak landslide source, but unfortunately, we have no data with high resolution bathymetry in Sarawak. Maybe we want to use the GIMCO 08. And this is the parameter between GIMCO, Batnas, Demnas, UFV, LiDAR, and it's the resolution is very different, yeah, between GIMCO 470 meter for resolution and for the LiDAR 3 meters. This high resolution is very, very effective for the tsunami simulation. We also made some observation for the Gunung Anak Krakatau from the 2018. We have many reference journals about this event, so we can make the models and can make we can correct our model to the journal and from the imaginary satellite. Yeah. This one we tried at the time. We used the integrating between Batnas and Demnas. Yeah, we disappear the wet dry for the Demnas, and we disappear the dry position for the Batnas. Yeah. We have to consider about the direction by looking at the source of the landslide itself, yeah. Like this in the Gunung in south of the Ambon, yeah, in Ternate, Gamalama. From high resolution, we can get the good data, yeah, good data and good tsunami map. Oh, sorry. Yeah. This last one. 2 months ago, I went to the Karangetang from north of Sulawesi. Yeah, we because of in Karangetang, Sulawesi, there is only BAPNAS data, so we have to make some GPS survey to collect the data from GPS to complete the topography. And for bathymetry, we conducted the sailing, using the simple fisherman, fish finder, Fish finder is very simple, but it's the accuracy is nearly same to the multi-beam echo sonder, as what we just said from the beam. Yeah, and when I running the simulation, I ran for 4 days for this Siau island, and just morning I just get the results. With the resolution I make the 0.001. So that's the difference. The maximum tsunami amplitude is lower than BAPNAS when we use the integrating between BAPNAS, SRTM, and field survey. Okay, this is the only draft interim result, and I still found the fantastic result. In the source centimeter, I want still make the correction from the expert. And this tsunami hazard map we produced from BMKG, more than 250 pieces in BMKG, and also we collaborate to ITS, 30 pieces. This is the comparison between we use only no integration, and after integration between bathymetry and topography is different, and giving the wider impact, the maximum height is so different. There is place maybe higher or not, maybe slower if you use the integration data. And we use, for tsunami survey, we use tide correction. Is very useful because we can correct our result, for the survey. There is in Palu, at the time, our result is bigger than the other surveyors because we came at the first time 3 days after the event, so the traces of tsunami is still clear and there is no clean up from the government like military. We consider the timestamp of tide gauge. And for tsunami gauge is, thank you for BIG can deliver some all data of tide gauge, so we can make collaboration, and there are 298 BMKG, BIG, and KKP water level sensor. We can integrate to TWS and can be monitored on the IN10T display. And this year, BMKG provide 100 tsunami gauge with 1 second sampling for the weekly confirmed tsunami warnings. And this is existing condition, as I already saw in the last previous slide. There is easy web and tsunami web, and it's still low resolution, only 1 kilometer with wide grid scale using GEPCO, not yet inundated, and scale only still province and municipality. And in the future, we want to make some detailed model with complex variation. Maybe from the first one, we use only one single segment, and we want to use the multiple segments. So it is very complicated, I think. And this is our challenge. Yes, intelligent repository, we have maybe big data, analytic IoT, and we have to use the artificial intelligence. So in 2005, we have to use GPSC, HPC, and GPUs. This is the comparison between when we use the only CPU or the GPU. It can scale up, the resolution. We can reduce the time, from the hours to the minutes. As my experience, I run model 4 days from Saturday until this morning. Maybe from GPU I can run only several minutes. So the last is summary my recommendation. Overall, we need the high resolution of topography maps, land cover, MSL lines, number of nested modeling grids, and the future, yeah, we need the HPC and GPU is very important. If we have the data like LiDAR, UAV is very, very good for tsunami modeling. And the availability of big data in the Eastern Indonesia region is still scarce. Yeah, it's very necessary to provide this disaster mitigation service in that region. Yeah, there is. I didn't found in several regions about DEMNAS in Eastern Indonesia. So that's why we have to collaborative data sharing between institutions holding high resolution data between government agency and overseas is very necessary to create higher quality disaster maps. Thank you.
Thank you, Dr. Sugain, for sharing with us the supermarket of disaster and the different characteristics, different types of the disasters and the size of disasters. So we can see that in order to study, in order to model, to simulate, to provide early warning, the use of multiple technology, the use of multiple source of data, and these are geospatial technology that is required to provide the inputs, to provide the necessary data for the study. And also I think you have highlighted the needs for collaboration, both land and sea agencies together, gathering all the data necessary to meet the challenges of disaster. Thank you for sharing with us on that. So now I would like to open the floor for question and answer. I think first I see Everett. I give the floor to Everett for a question.
Thank you, Victor. So, Everett Mulder, Singapore Land Authority. My first question was actually also the definition from Matthew. I guess you get our perspective on that, or our favorite in a way. Perhaps it could be a thing that UN-GGCE comes up with, like a globally accepted definition, so that we all know what we're talking about. Perhaps that's an idea. But my question was more in general to, I suppose, mostly for Matthew and Basara-san. You're talking about resolution, and Matthew mentioned that you, for your case, you focus more regional and national, so your resolution is perhaps not as high as you would want it. But if you think about it conceptually, what would be a good resolution to have? On one hand, you could say the higher the better, but is it really necessary? What would be a good fit that kind of like balances everything? So that's my first question in general to the group. And second question is, how do you deal with different tidal datum heights? I believe it was mentioned that you could shift it, but what do you shift it to, for example? Do you all shift it to a common level? Then what level do you choose? Or do you smoothen it out perhaps? Yeah, could you share your view on what you could potentially do in that area? Thank you.
Thank you, Everett. Matthew?
Yep, thank you very much for the question. So the first question there about resolution, the way that we address that issue is we sort of looked at our continental shelf as our guiding point there. So we define coastal water as on the shelf, and that's where we produce the grids at the 30-metre resolution. And then we have a larger grid that overlaps that coastal 30-metre grid but extends out past the shelf. So a much larger size, but that's only produced at the 100-metre grid resolution. So that's the general way we've done it. It doesn't quite work everywhere in Australia. You know, you'd appreciate that on our western coast, our continental shelf extends extensively. On the eastern coast, it drops off rapidly. But we sort of found that for our use cases, that really was what worked. And I guess how we decided on those numbers is really looking at use cases. We looked at what does the government need to achieve, what's the minimum required resolution to achieve those uses, and then also what data do we have and what can the data support. If we had full coverage multi-beam and bathy LiDAR, we could be producing some crazy grids and capturing some crazy geomorphology, but we're not quite there yet. So that's sort of what guided our journey. Did that answer the question?
Yes, thank you.
Thank you.
Thank you. Sarah, you have anything to add to the question?
Thank you for question. So your question is regarding the
resolution.
Resolution.
Yeah, so my first question would be, what would be an ultimate resolution that you would want to have? Like what does kind of tick all the boxes? And then my second question was about the tidal height differences with respect to the land.
Okay, so our resolution, in Japan, our effort is still best effort. So we just continue to develop the highest resolution as possible, but our resources, of course, limited. So we are having a conversation with different stakeholders. What will be the most optimal resolution for different stakeholders? But still, our effort is a best effort basis from technical perspective. Second one is tidal. Sorry, I still cannot.
Yeah, so around your country, as every country, the tidal characteristics will differ, right? So the tidal heights, different location will differ. So you would have different tidal datums around your country. So how do you need to integrate land and sea, but you also need to deal with the fact that the tidal datums around your country are different, right? So how do you go about that?
Actually, so maybe can you, Sumio-san?
Okay, I'm Masano Sumiyoshi, and now working in IHO, but so I was working in Geoid, so I answer the question. Unfortunately now we don't have a rough solution, but in the future the data we have what to say when the ERS survey and the vertical chart data is established, then we have a WGS84 reference. We have a reference. So using this one, we can convert the ocean data to the WGS84 and Geoid. So this is our my understanding now. Thank you.
Thank you. Thank you. And of course, I think we hear that at this point of time, the resolution is really based on best effort, what the data available from the different sources. And moving forward, and I also hear that it is also use case driven as well, right? And that is also the same challenge in Singapore, that we are trying to ask user what resolution do you want, and there is really very little input back to the question. Yeah. Any questions from the floor? I would give the floor to Professor Ramon. I see you first.
Thank you very much.
Thank you.
I have a question to Matt Ellis. I was very interested how you explained the difference between a morphological approach and something that you call geodetic control. And I was thinking about that, whether that is now kind of really like a new way of looking at it. And actually my question is, so is the difference between a morphological approach versus a geodetic approach, is that in your eyes mainly the size of the error bars? Because I would argue that even if your data may be not so good, I mean, also in Geodesy we can deal with large error bars, right? So is it really like a different approach, or is it really just another way of saying that the data are of different quality and it could be better?
Thank you for the question. I do actually think that fundamentally it is a different approach. Obviously, that's a really great point that we can just capture error as a secondary product for our grid. But really, a lot of the use cases for these, morphological integrity-based grids, the shape is paramount. Having artifacts, for example, that you might find in a GEBCO-style grid really is detrimental. And so what, the manual interventions I was talking about, and this sort of addresses the first question where I didn't talk, maybe address it, is we don't just do geodetic shifts. We will then manually look at two data sets. If one of them is going to, negatively impact the shape of our seafloor, we will just grab all those points and shift them 10 meters to match. That is why it doesn't have that geodetic control, because we are doing that extra step beyond our sort of geodetic and tidal datum shifts to then go, this is not going to fit our grid, we're going to force it in a way that preserves the shape of the seafloor. So I think that might answer your question of how it varies from just a geodetic approach like a GEBCO style grid.
All right. Yeah, my counter argument would be that it is, in geodesy we are not only having precision and error bars, we also have biases, right? So, and in a way a shape is nothing more than positions with a scale factor that is unknown, right? So my argument would be that it is actually, I'm not sure whether it has a big effect by calling it like a totally different approach. I think it would make, in my opinion, more sense to bring it into the geodesy realm and try to estimate, for example, the scale factors or the biases that we're involved with. Yeah.
That is a great point, and I guess I on some levels agree. And what Geoscience Australia is sort of doing in this space is we hope that in the future we can, as our geodesy improves, incorporate that into this product. But our sort of main argument here is that what we're doing is what's possible right now, and there will be geodetic improvements going into the future.
So I guess a lot of the things that we are doing now is at the best effort stage, and improvement are required going into the future. Yeah, I'll give the floor to the other gentleman there. Yeah, yes.
Thank you. I would like to ask some questions to Dr. Sugeng. The first one about the resolution of the bathymetry and topography data for the tsunami modeling. You said you integrate the DEMNAS and BATNAS because it is very different in resolutions. BATNAS we have about more than 100 meters, and then in DEMNAS we have 8 meters resolution. How do you combine or integrate those two data? And then the second one related to the land use, because you mentioned about the effect of the land use to the simulation resolution to the tsunami simulations. I believe it is about roughness when this is run up to the coastal area. So I mean also the resolution about this land use. What type of land use will be impacted to the run up of the tsunami? Okay, thank you.
Dr. Sugeng.
Okay, thank you, Pak Wiwin. Thank you, Pak Wiwin. Yes, for integrating bathytopo, different resolution from 473 meters, integrate with 8 meters, but it must be done because we need the bathymetry, BATNAS for bathymetry data is very accurate for the data, and we use the topography from DEMNAS used for inundation. So after that we have to combine that one into a single map, so it can the tsunami can come through the from the beach to the land, and it is the inundation. how to integrate? Yeah, the first one we have to throw out the wet from the topography and the dry from the BATNAS, because there is data and plus and negative, positive and negative, and both of data, and then also we have to combine the MSL lines. Yeah, MSL line. This is for the zero contour. Yeah, it's also the product of the BIG, and beside that, we also to make some what we say. There is a border. Even we already throw out the wet and dry. Yeah. How the resolution? Yeah. I don't know how to say that, because it's good. Very difficult question. Not the different resolutions of how we can combine this. Yeah, maybe at this time I couldn't answer this question. Yeah, but this is what we get from the from BIG and from BRIN, and maybe their colleagues.
If I can help, I think again this is very early stage. A lot of things are still trying out best.
Yeah, it's just
I mean, similarly, I would have the same question as in: is there a need after joining them, Topobati?
Yeah.
Is there a need to do a validation on the ground?
Yeah.
And if there's a need, how do we do it? How do you prove that what you have produced is fit for purpose or is up to the mark? So I think these are the questions that we probably no answer yet, or do we have an answer? Any comment?
Yeah.
Maybe.
Yeah.
Do we need to go and prove that this is a good model to meet the usage?
Yeah. There is some procedure also how to combine this, and by make some smoothness between border. Yeah, if there is no smoothness, so the tsunami head will be blow up. Yeah, yeah. Okay. And the second one about what the roughness type, what we use in our simulation. Yeah. We use the mining roughness. We can from the RBI maps from BIG, there is a coordinate from every location. The coordinate can show this is the forest, or this is the village, this is the building. So we can put the point from the land use. Yeah. Okay, thank you.
Various methodologies or different approaches to integrating land and sea. So my question here, more from the layman perspective, is in terms of, is there a need for a consistent methodology or certain standards in terms of how we integrate land and sea? Why am I asking this question? It's because if everyone is doing it differently and on a global level, what will be the impact? So whether is there a need for a consolidated approach towards managing the marine and the terrestrial domain? Thank you.
Well, I'll go ahead and take a stab at that one. I think we're actually going to try and cover that one in the next session. But the intent is that IHO, OGC, and ISO are all working towards trying to come up with common standards. And there are a lot of projects where they're making efforts to try and come up with something along those lines. I would say nothing's definitive at this point, but the intent is that those standards bodies are working together. I actually was going to try and present some of that, as I said, in the next set of presentations. So if you can be patient, then hopefully your questions will be answered.
Okay, that's great. Perhaps I'll just, another recommendation that perhaps the UN-GGCE could also look into one of this potential area of work, where is there a need to have a common framework in terms of how we integrate land and sea. Thank you.
Okay, thank you. Thank you for, this is akan datang, next session. Yeah. I still have time for one last question from the floor. Okay, I'll give the floor to Perry, maybe. Yeah, Perry, go ahead. Yeah. Two questions I can take. I think we still have time.
Okay, I have half a question. For actually Basara, You mentioned the Kuroshu Island complicates your measurements, your mean sea level. Kuroshu Island, what is the current 2 knots? Is it, what is the limit which your current is that makes it complicated? Is it just the speed?
The dynamic ocean topography generated by the current varied temporal variation. So the shape of the topography changed year to year. So this is very challenging. We need to track the change. So this is a challenge.
Thank you. And Jonathan, your question? Yeah. Pass a mic for Jonathan.
Thank you. So we know that some vertical datum has tilt or are distorted because the use of only one tide gauges as origin, or by the use of several tide gauges mean sea level constraints above the country. But we know that it can provoke distortion in the vertical reference frame. So how can we deal with this when sometimes you don't use a dynamic topography to correct mean sea level and to go back to Geoid? I know that Australia has corrected its north-south tilt of the vertical datum by the use of dynamic topography, and I am currently working on this for France because we have a very huge slope from Marseille, where is the origin of the vertical datum to the north. And I think it is an important issue to correct, to deal with dynamic topography, and products are available from space altimetry and oceanographic in situ measurement. And I think for the continuity of data and information, it's important to use what is available, dynamic topographic products. And I understand that at the time where our vertical datum were produced, some decades or centuries sometimes, dynamic topography was not available. We know the concept, but we didn't know that, how much it was. But now we can use it to correct our vertical datum and to access directly and continuously to the geoid from land to the sea.
Thank you for the comment. Question? Any comment from the panel? Yeah.
I'll take it. The other thing Basara could as well. This is one of the reasons we're moving to gravimetric geoid-based data, is that we can calibrate. And as I showed in my slides, we did pick all the tide stations, and we did try to account for the topography. I can tell you that we are moving in that direction because our terrestrial leveling datum had a 1 meter, 1.5 meter tilt to it. And you're not going to get, it's not just that you picked a bad tide station, it's that the accumulated leveling errors when you're traveling 8,000 kilometers and doing a massive adjustment, you're going to accumulate errors. The example we give is if you're standing in Seattle, Washington, and you're standing at 0, according to the North American vertical datum of 1988, you're about thigh high deep in the water. So it makes it problematic to try and use that for coastal inundation modeling. So this is one of the reasons we've been moving to these geoid-based models, because on the scale of a continent, the satellite models provide a lot of that stabilizing force that makes sure that you get the match, that you do not have that meter level tilt across a continent. Then you need the fine-tuning. You do need to bring in the tide stations and calibrate against them. We'll go further. We're actually looking at the Great Lakes as level surfaces. We're actually to the point where we think that each of the lakes is at a different equipotential surface. It's not the geoid, it's elevated above it, but they're equipotential. And when we go through, we're actually seeing agreement in the ±2 centimeter range when we use GNSS and the geoid model. The next step will be to start to come up and down all the riverways, because there the dynamic heights should be going down, ideally. If they go up, then we have a problem. But they should be going down to the sea. So the intent of all of this is to use these models to calibrate from coast to coast, across regions, across islands, like in Indonesia, to get the continuity between the different islands, to have the same datum, and to try and eliminate, or at least be able to model some of the impacts of the topography, the ocean dynamic topography of the sea surface. Much the same issue with the Kuryoshi current we have with the Gulf Stream. It's plus minus a meter, and it makes it a significant problem, and we have to account for it up and down the coasts of the east coast of the U.S. So it is a factor, and that's why when you saw, you can produce models to describe it, and you can incorporate that. So you can express heights above local mean sea level, which is what you would want for a tsunami. You would want to know where the local mean sea level was, any tidal variations around that, and then you could project where the waters might go in, and then you maybe have your flood evacuation routes to figure out how to get people out. So.
Thank you. Basara-san, you have anything to add?
I'm done already mentioned about one thing that so we are still continuing to use the single reference local sea level as a reference for whole the country, just because we are already using the height constructed from geodetic leveling, and we need to keep continuity as much as possible for users. But we also need to provide the relationship with the local height to the national definition of the height. And hopefully we will provide a transformation parameters to these systems.
So thank you. We are at the end of this session now. Thank you all for your participation, for your questions. I think it's a very active discussion. And please put your hand together to thank the speakers. Thank you very much. I'll pass the floor back to the lovely
Thank you,
MC.
Mr. Koo. Ladies and gentlemen, please give a big round of applause for all of us once again. Thank you, Mr. Koo, for leading us through such a productive and engaging session. We truly appreciate your time and expertise. Now, with all due respect, I would like you to deliver the token of appreciation to all the speakers. Gentlemen, please come forward to the stage. Okay, now for the last photo. Please give your best smiles to the camera. Thank you. Please give a round of applause for all of us once again. To Mr. Koo, all respectable speakers and moderator, you may all return to your seat. Okay, distinguished guests, ladies and gentlemen, we have 30 minutes for morning break. Refreshment is available at the pre-function area. We kindly ask you to return to this room at 11 a.m. to continue to the next session. Thank you and enjoy.
The moon and let me play.
When do the tides change across Indonesia? Where are the locations of Indonesia's hotspots and ring of fire? Where are the locations for development that are deemed safe from natural disasters and can be used to develop a disaster mitigation system? When the public requires answers, decision makers looking for the geospatially based big picture as a base for all geospatial information layers. We are here. BIG has transformed substantially from 1938 to 2011. Their roles and responsibilities in the field of geospatial in Indonesia have grown so that they can stay relevant.
Kalau dia dikecilin dikit bisa nggak? Saya ngetes sama dia.
Ultimately, in 2011,
Cek. Ya. Cek. Ada ya, sih. Okay.
Partnership with the Ministry of National Planning and Development. BIG holds the roles of regulator, implementer, coordinator. We prepare the data and regulation while also implementing them at the same time. As a regulator, BIG is responsible to prepare development policies for geospatial information. As an implementer, BIG has a duty to provide a complete spatial information, a digital system to collect various geospatial information that is accurate and integrated with the national and global coordinate systems. We own geodetic information, or the mapping of the Earth's surface, regional physical objects data, position determinant data, seismic activities data, tidal observation data, meteorology and ionosphere layer data. All is available to use as a starting point to develop Indonesia, which encompass natural resources, infrastructure, disaster mitigation, economy, research, tourism, state defense, and security. In doing their role to compile strategic mapping, BIG always works hand in hand with the associated government bodies. We are partnered with as many as 19 ministries and 34 regional governments. Our duty is to prepare spatial policies that refer to the One Map policy. Guaranteed access to information. Credible information. Proper. That is the quality of information from BIG. That is how we participate in the governing of and in the geospatial literacy of Indonesia's society.
Data becomes one of the precious assets in this digital information era. Including geospatial data play a role to support decision and policy making through comprehensive analysis. As an example, geospatial information that has been processed from geospatial data can be used to support Sustainable Development Goals, or SDGs, in Indonesia. Geospatial information may be used to formulate policies and carry out geospatial-related activities. Why is geospatial data necessary to support SDGs? Indonesia has enacted Presidential Decree or Perpres number 59 of 2017 on implementing the achievement of SDGs. This regulation states that National Action Plan or NAP of SDGs should be synchronized with National Midterm Development Plan. According to the SDGs target, Indonesia's SDG achievements rose slowly between 2016 and 2020. Then, Geospatial Information Agency or BIG, with its competency in data processing and geospatial information, formulated a geospatial information roadmap for Golden Indonesia by 2045. BIG will integrate geospatial and statistical data to be processed into spatial data. Through a One Data, One Map policy, the integration among social welfare, inclusive economy, and habitable environment will realize sustainable development in Indonesia. The role of geospatial information in the SDGs. Implementations of geospatial information to support sustainable development are 1. Organizing a competition of geospatial-based application development to support SDGs, which is available to all Indonesian students. 2. Creating prototype of SDGs mapping at village level by integrating statistical and spatial data. The result will be reported in the UN-GGIM AP Working Group 3 forum. 3. Mapping the area of rice fields throughout Indonesia by means of the natural resource balance method. This accurately mapped data will give an impact on the effectiveness of the state budget revenue and expenditure, including subsidy of fertilizer, agricultural tools, and seeds. Balance mapping of natural resource has been also used for other commodities, for instance, palm oil and corn. Through one map policy in Indonesia, we expect all existing data can be visualized spatially and integrated for each part in the sustainable development. Therefore, Golden Indonesia can be achieved.
Indonesia, the largest archipelago in the world, ranked as the 4th most populous country with a great number of islands, spatially very diverse and a high degree of complexity among its populace. These complexities strongly influence various aspects of development in Indonesia. State policies must also be drafted in a thoughtful and equitable manner, encompassing all aspects of life. It is of primary importance to advocate for the people of Indonesia's welfare. It is for that reason the issue of sustainable development became crucial. The United Nations has actively encouraged Indonesia to implement policies that are oriented towards Sustainable Development Goals or SDGs in national development. On September 15, 2015, as a member of the United Nations, Indonesia, along with other 192 member states, agreed to the SDGs. SDGs need the support of statistic data integrated with Indonesian geospatial data. The Indonesian Statistical and Geospatial Framework, or ISGF, was established to turn that into reality. ISGF comprises all of the collected village borders data in Indonesian regions, provided by the Geospatial Information Agency. In 2019, mapping was concluded and integrated with statistics from ministries or other agencies which are also part of the ISGF program. The ISGF program will be continued into 2020. At the moment, the discussion over concepts, data collection, and prototype development are still ongoing. BIG is responsible to deliver the ISGF platform by the year 2024. ISGF is expected to become a role model in the development programs for Asia-Pacific countries and to further develop into a global statistical geospatial framework. What is the distribution of Indonesia's natural resources? Where are the locations of Indonesia's nature tourism potentials? When do the tides change across Indonesia? Where are the locations of Indonesia's hotspots and ring of fire? Where are the locations for development that are deemed safe from natural disasters and can be used to develop a disaster mitigation system? When the public requires answers, decision makers looking for the geospatially based big picture as a base for all geospatial information layers. We are here. BIG has transformed substantially from 1938 to 2011. Their roles and responsibilities in the field of geospatial in Indonesia have grown so that they can stay relevant with the current day and age. Ultimately, in 2011, our agency was born, along with the enactment of the Spatial Information Law. The Geospatial Information Agency is directly under the President of the Republic of Indonesia, in partnership with the Ministry of National Planning and Development. BIG holds the roles of regulator, implementer, coordinator. We prepare the data and regulation while also implementing them at the same time. As a regulator, BIG is responsible to prepare development policies for geospatial information. As an implementer, BIG has a duty to provide a complete spatial information, a digital system to collect various geospatial information that is accurate and integrated with the national and global coordinate systems. We own geodetic information, or the mapping of the Earth's surface, regional physical objects data, position determinant data, seismic activities data, tidal observation data, meteorology and ionosphere layer data. All is available to use as a starting point to develop Indonesia, which encompass natural resources, infrastructure, disaster mitigation, economy, research, tourism, state defense, and security. In doing their role to compile strategic mapping, BIG always works hand in hand with the associated government bodies. We are partnered with as many as 19 ministries and 34 regional governments. Our duty is to prepare spatial policies that refer to the One Map policy. Guaranteed access to information. Credible information. Proper. That is the quality of information from BIG. That is how we participate in the governing of and in the geospatial literacy of Indonesia's society. implications of Indonesia's nature tourism potentials? When do the tides change across Indonesia? Where are the locations of Indonesia's hotspots and ring of fire? Where are the locations for development that are deemed safe from natural disasters and can be used to develop a disaster mitigation system? When the public requires answers, decision makers looking for the geospatially based big picture as a base for all geospatial information layers. We are here. BIG has transformed substantially from 1938 to 2011. Their roles and responsibilities in the field of geospatial in Indonesia have grown so that they can stay relevant with the current day and age. Ultimately, in 2011, our agency was born, along with the enactment of the Spatial Information Law. The Geospatial Information Agency is directly under the President of the Republic of Indonesia, in partnership with the Ministry of National Planning and Development. BIG holds the roles of regulator, implementer, coordinator. We prepare the data and regulation while also implementing them at the same time. As a regulator, BIG is responsible to prepare development policies for geospatial information. As an implementer, BIG has a duty to provide a complete spatial information, a digital system to collect various geospatial information that is accurate and integrated with the national and global coordinate systems. We own geodetic information, or the mapping of the Earth's surface, regional physical objects data, position determinant data, seismic activities data, tidal observation data, meteorology and ionosphere layer data. All is available to use as a starting point to develop Indonesia, which encompass natural resources, infrastructure, disaster mitigation, economy, research, tourism, state defense, and security. In doing their role to compile strategic mapping, BIG always works hand in hand with the associated government bodies. We are partnered with as many as 19 ministries and 34 regional governments. Our duty is to prepare spatial policies that refer to the One Map policy. Guaranteed access to information. Credible information. Proper. That is the quality of information from BIG. That is how we participate in the governing of and in the geospatial literacy of Indonesian society.
Becomes one of the precious assets in this digital information era. Including geospatial data, play a role to support decision and policy making through comprehensive analysis. As an example, geospatial information that has been processed from geospatial data can be used to support Sustainable Development Goals, or SDGs, in Indonesia.
Ladies and gentlemen, we are about to begin the next session shortly. So we need all participants to be back to the main room.
Indonesia has enacted Presidential Decree, or Perpres, number 59 of 2017 on implementing the achievement of SDGs. This regulation states that National Action Plan, or NAP, of SDGs should be synchronized with National Midterm Development Plan. According to the SDGs target, Indonesia's SDG achievements rose slowly between 2016 and 2020. Then, Geospatial Information Agency, or BIG, with its competency in data processing and geospatial information, formulated a geospatial information roadmap for a golden Indonesia by 2045. BIG will integrate geospatial and statistical data to be processed into spatial data. Through a one data, one map policy, the integration among social welfare, inclusive economy, and habitable environment will realize sustainable development in Indonesia. The role of geospatial information in the SDGs. Implementations of geospatial information to support sustainable development are 1. Organizing a competition of geospatial-based application development to support SDGs, which is available to all Indonesian students. 2. Creating prototype of SDGs mapping at village level by integrating statistical and spatial data. The result will be reported in the UN-GGIM AP Working Group 3 forum. 3. Mapping the area of rice fields throughout Indonesia by means of the natural resource balance method. This accurately mapped data will give an impact on the effectiveness of the state budget revenue and expenditure, including subsidy of fertilizer, agricultural tools, and seeds. Balance mapping of natural resource has been also used for other commodities, for instance, palm oil and corn. Through one map policy in Indonesia, we expect all existing data can be visualized spatially and integrated for each part in the sustainable development. Therefore, Golden Indonesia can be achieved.
Indonesia, the largest archipelago in the world, ranked as the 4th most populous country with a great number of islands, spatially very diverse and a high degree of complexity among its populace. These complexities strongly influence various aspects of development in Indonesia. State policies must also be drafted in a thoughtful and equitable manner, encompassing all aspects of life. It is of primary importance to advocate for the people of Indonesia's welfare. It is for that reason the issue of sustainable development became crucial. The United Nations has actively encouraged Indonesia goals or SDGs in national development. On September 15, 2015, as a member of the United Nations, Indonesia, along with other 192 member states, agreed to the SDGs. SDGs need the support of statistic data integrated with Indonesian geospatial data. The Indonesian Statistical and Geospatial Framework, or ISGF, was established to turn that into reality. ISGF comprises all of the collected village borders data in Indonesian regions, provided by the Geospatial Information Agency. In 2019, mapping was concluded and integrated with statistics from ministries or other agencies which are also part of the ISGF program. The ISGF program will be continued into 2020. At the moment, the discussion over concepts, data collection and prototype development are still ongoing. BIG is responsible to deliver the ISGF platform by the year 2024. ISGF is expected to become a role model.
Distinguished guests, ladies and gentlemen, the event is about to begin. I kindly request to all of you to be back to the room and have a seat. Thank you.
Of Indonesia's natural resources. Where are the locations of Indonesia's nature tourism potentials? When do the tides change across Indonesia? Where are the locations of Indonesia's hotspots and ring of fire? Where are the locations for development that are deemed safe from natural disasters and can be used to develop a disaster mitigation system? When the public requires answers, decision makers looking for the geospatially based big picture as a base for all geospatial information layers. We are here. BIG has transformed substantially from 1938 to 2011. Their roles and responsibilities in the field of geospatial in Indonesia have grown. so that they can stay relevant with the current day and age. Ultimately, in 2011, our agency was born, along with the enactment of the Spatial Information Law. The Geospatial Information Agency is directly under the President of the Republic of Indonesia, in partnership with the Ministry of National Planning and Development. BIG holds the roles of regulator, implementer, coordinator. We prepare the data and regulation while also implementing them at the same time. As a regulator, BIG is responsible to prepare development policies for geospatial information. As an implementer, BIG has a duty to provide a complete spatial information, a digital system to collect various geospatial information that is accurate.
Ladies and gentlemen, the event will begin shortly. I need all of you to have a seat.
Information or the mapping of the Earth's surface, regional physical objects data, position determinant data, seismic activities data, tidal observation data, meteorology and ionosphere layer data. All is available to use as a starting point to develop Indonesia, which encompass natural resources, infrastructure, disaster mitigation, economy, research, tourism, state defense, and security. In doing their role to compile strategic mapping, BIG always works hand in hand with the associated government bodies. We are partnered with as many as 19 ministries and 34 regional governments. Our duty is to prepare spatial policies that refer to the One Map policy. Guaranteed access to information, credible information, proper. That is the quality of information from BIG. That is how we participate in the governing of and in the geospatial literacy of Indonesia's society.
Okay, ladies and gentlemen, now we have come to our next agenda, the sixth session, Standards, Policies, and Legal. This session will be moderated by the distinguished expert, Dr. Perry Oy. Let's give a big applause.
Hello, this is like Academy Awards. Anyway, I hope you're not sick of hearing my voice or seeing my face. Anyway, this is a sixth session. You only have to tolerate me for 1.5 hours, okay? Anyway, let me just, before we start our session, recap what has happened the last 1.5 days. I think the most important thing, we have seen use cases. And from the use cases, we found that there is a need for good quality, consistent, harmonized data. And how do we do that? We need standards. And that's where I think this session is quite timely, gets to that place. And this is also interesting. We have, before I get into the 4 presentations, it's also interesting because from this session, hopefully you will use that information where you can justify to your decision makers the points, because it will not only cover standards, but it also covers the use cases for you to help justify. And we have a, okay, so if we go into today's presentation, you know, I'm getting old. Okay, today's presentation, there will be 4 papers. One is on standards consideration for members, and this will be delivered by none other than our great Dan Roman. Okay, I don't need to introduce him anymore. Okay, that saves me 1 minute of our time. Okay. Second, our Honorary Pak Arif. I don't have to introduce him as well. By the way, they did a great job last night. As a result, this morning I didn't have to swim extra laps. And the third presentation will be a guest speaker, Christopher Body. His subject presentation will be Connecting Land and Sea Federated MSDI Pilot and the 19152 on Land Administration and Domain Module. Okay? He's your special inclusion for today's presentation. Last but not least, unfortunately, Ilaria Tani, she is the professor from the Milan University. She can't make it because she has some previous engagement. But we got her online. It is 5 o'clock in the morning. She woke up at 4 o'clock to make sure that she's awake for 5 o'clock, but I hope she's online now. I hope she has not gone back to sleep. Okay, good. Okay, so without much more to say, can we invite our great Dan Rowan to share with us about standards. Ben.
Good morning again. So I'm going to speak to a couple of items here to talk a little bit to the use cases and then get into some of the standards. So use cases. Joining land and sea is problematic given the breadth and the variety of geospatial data collected on the earth, undersea, and in space. Daily, all of this data is collected in a consistent, accurate global coordinate reference system. However, different coordinate reference systems are preferred on land versus sea, the ITRS versus WGS84. GPS is a U.S. military system intended to position, navigate, and target in the WGS84 coordinate reference system. It is a dynamic coordinate reference system, meaning that the coordinates change with time. So the coordinates of land-based or onshore facilities would then continuously change with time if you're using WGS84. This is problematic for a lot of applications that we need to either know where they are and know how they're changing, or at least be able to go back and replicate them. The difficulty with WGS84 is it's always operating in the now. It's always being updated, and it'll tell you where you are now and where you want to go now. But if you've mapped anything historically in it, then it becomes problematic. So the adoption of it as a standard is an issue. And keep in mind that GPS is only one of many GNSS. So you're already self-limiting when you're in the GPS only to the WGS84 system, and you're excluding all the other GNSS if you're not necessarily incorporating them. So the ITRS is preferred to better understand the transition from sea to shore for coastal resilience and commercial activities. So then what are needed for global efforts? The UN-GGIM provides a little bit of context. So as Nick's kindly informed me on a couple of occasions, the UN does not tell sovereign nations what to do. They're there to help the sovereign nations. But a lot of the resolutions that are put forth and voted for by the member states talk to some of the frameworks and other aspects about how they want to organize themselves to get all of the geospatial data organized. The broader mission of the UN is to maintain international peace and security, but this includes solving international problems of economic, social, cultural, or humanitarian character. So the UN resolution regarding the UN-GGIM was about how to bring all the geospatial data sets, all of these different data that I addressed at the outset, bring them together to try and describe how they could be interrelated between nations and within regions. Recognizing the need for this underlying geodetic underpinning to all of this geospatial data, the UN created the GGRF, the Global Geodetic Reference Frame, which included geodetic standards and conventions. So you're going from the UN-GGIM, where they talk about frameworks and standards, to a reference frame, the GGRF, that talks about standards and conventions. And in particular of note in there, they also address coordination with the International Association of Geodesy, with that being an implication then, although not explicit, that we should be looking to the ITRS and not necessarily to WGS84. So, to recap, hopefully some of you were present at the 14th plenary, but there were a number of things that were ongoing. One of which was, of course, this form, which is a continuation. The form that was there, this is a continuation of that series. There's a lot of discussion about how to bring the terrestrial and maritime domains together. That one preceded, was just ahead of, the one Nick had put on with the forum on the joint plan for the Global Geodesy. Sorry, I'm flustered there a little bit. But the point is that what we're looking for is the adoption of something for Global Geodesy to build this geodetic infrastructure and workforce. And to that end, then, we're looking to align all this geospatial data to make it interoperable, both in terms of the way the data are organized, in terms of standards, in terms of like 19115-2, which is an ISO standard, but also in terms of the reference systems in which the data sets are aligned and how and where to be able to do data transformation to accomplish that. To accomplish that integration of these domains means we need consistent standards that need to be developed, but we need to do so across multiple domains, across the maritime and terrestrial domains and the cadastre. So, as I mentioned, there was a standards body met during the UN-GGIM 14th plenary. I encourage you strongly to read the report. They put forward an item that discussed the various areas in which they're collaborating. IHO, ISO, and OGC all have different components, and I'll talk to them next, but it's important that you take a look at these, because these three bodies are working to collaborate together to try and devise standards to bridge the land and the maritime domains. So if you look through the report, you can see areas where they're engaging. These are opportunities for your countries to likewise join those efforts. And I'll take a moment to encourage you to participate in all three of these organizations, to send bodies to participate in these standards. The best way to make sure a standard is written in a way that you can accept it is to be a member of the committee that is writing the standard. I can't emphasize that enough. And most of these, particularly with ISO, they're looking for national representatives. You can have private sector and others engaged as well, but most of the authoritative members are from countries. And if you don't send your members, then they're not participating, and you don't necessarily gain the full weight of being able to influence the documents. So, first, ISO, Technical Committee 211 specifically, I'll talk to. Provides a bulk of the different standards related to geospatial data. It's geospatial and geomatics types of information. Sampling of them that are up here, I will emphasize things like 19127, which relates to the ISO Geodetic Registry. I'll come to that one later. The ISO Geodetic Registry is Advisory Group 12 is the one that manages that, but AG12 administers what is in the ISO Geodetic Registry. That is where nations put their authoritative definitions for their datums and the appropriate transformations. That's where it is preferred that GIS professionals go to pull it, because that is where the nations say that is the correct one. I say this because later on I'll talk to you about the EPSG's Geodetic Registry, and I can tell you that Roger Lott, the manager of that, is very interested in making sure that for authoritative reasons, if you're going to do things like charting, that they would prefer you to go to the ISO GR. But in addition to 19127, you can see some of the others, 19111, and then some of the other standard ones. The first two, I would also note, are currently in review, so we're looking to rewrite them again. It typically happens about every 5 years. So TC20. So I talked a little to ISO TC211 because a lot of that covers a lot of the geospatial and geomatics types of positioning, and a lot of the geodetic aspects fall underneath that. TC20 has authorities over aircraft and space vehicles. Those space vehicles would include GNSS satellites. They have put forth a number of standards, ISO 24246, that says that if you receive GNSS signals, that you have to do things their way in terms of how you organize cores on the ground and organize your reference systems for autonomous vehicles. That is a bone of contention between 2C211 and TC20. So even within this technical community, you should not think that it's monolithic, that there are different groups that are needing to coordinate their activities. And finally, TC204, Intelligent Transportation Systems. That is intended right now for onshore, for autonomous vehicles navigating down the road. But it could include autonomous shipping pulling in, autonomous aircraft. Trying to coordinate between these three to get appropriate standards just within ISO is a challenge, but it is one that they're working to try and coordinate. At the plenary meeting, when we did meet, we talked to some of these issues and we worked through them with an eye to trying to coordinate, at least from the ISO side of things, how they're going to try and address these issues, how to bring in signals from space to include ground-based augmentations to do precision and accurate navigation and positioning. So I'll take a moment to digress because I've talked about it enough times in terms of the IAG. So it's been mentioned, and I think Antonius, I think you may have mentioned it before, but the ITRS takes in a number of pieces of information to monitor not just where things are located on the Earth, but the deformation associated with it. WGS-84 only has maybe a double handful of stations to monitor the entire planet. The IGS provides a wealth of more stations and does a much better job of describing the motion and provides a better basis for it. But in addition, complementary to that is, admittedly it's still nascent, the IHRS, International Height Reference System. So in my earlier presentation, I talked about taking GNSS and getting geometric coordinates and applying a geoid model. The global geoid model is what they're trying to get to, some type of international height reference system that everybody can get consistent heights tied to sea level globally. So this is why there was a discussion about coordination with the IAG, because they are developing admittedly more scientific and very persnickety models that are designed to try and address these very high level accuracy and requirements. But if they can meet those requirements, they can meet requirements that maybe have decimeter to meter level requirements for accuracy. But it provides consistency, and that is the biggest thing we're looking for in coordinates, is consistency and an understanding of the actual metadata that's associated with the datums and datum transformation. So then, back to discussion on the standards bodies, the OGC. So what's shown here is the White Ribbon Project. In the upper right-hand corner, OGC will have projects, and they'll have a number of different studies within those projects, and then eventually they migrate over into standards working groups that develop standards associated with these types of projects. And then they iterate back through again. Examples include the GGXF. I will tell you that that is a format for organizing geodetic data. The US and Canada are moving forward. I believe the Europeans are. There are a number of different groups that are moving forward to adopt this. Key for us in this is it's based on like a NetCDF type of format. A lot of our NOAA ocean models are in NetCDF. So I'm trying to get the NOAA models to be in the same format so that we have better integration of geodetic and hydrographic types of data sets. So that's just one example, but again, in this one, there is an ongoing project where they're starting to bid out, where they're trying to figure the best standards and requirements to go from sea to shore. So OGC is active in this, and so again, I encourage you to become involved and participate. IHO standards, S100. I'm sure most of us in here are familiar with them, but I will note in the right-hand corner, or in the right side, where there's discussion of ITRS versus WGS-84. WGS-84 decimeter to meter level in certain regions in terms of its precision and accuracy. For a lot of applications, in the middle of space or in the middle of the ocean or in the middle of the air, it's probably sufficient. But once you start to come up to the built infrastructure, once you start to come up to land, and that includes the land that's underneath the water, at the near shore shallow environment, and that in turn could also include landing on the moon or landing on Mars. You need to understand all the Earth orientation parameters that are built into the ITRS to get things successfully off the planet to where you want them to go. But it also applies to those things on the planet, to safely bring them in through port, over the shoals, under the bridge, pier side on time, not hitting anybody, and unloading all their cargo to the right spots on the pier and the drayage so that it can get on the correct car train or to the correct truck to go to autonomously to its destination. Those are not technologies that we necessarily have in place yet, but they are ones that could be in place if we come together with combined standards for getting merchant traffic from sea to shore. One thing I will note is that ISO, within ISO standards, they're using ISO 19111-2007. that's dated. In there, it only talks to static and does not allow for time-dependent positioning, so there are some requirements to the updates there. And then, as I touched on before, the EPSG versus ISO Geodetic Registry. Key here is that the two registries we took, when we created the ISO Geodetic Registry, we take basically a data dump from the EPSG registry. And Roger Lott, who manages the EPSG registry, sits on the ISO Geodetic Registry. There are links that put the entries for ISO Geodetic Registry and EPSG registry in each other's registries. So they're cross-linked. There's a lot of information, but the authoritative one is the one that is the ISO Geodetic Registry, is the one that should be preferred for use. EPSG would prefer you to use it because it reduces any liability. They are a commercial group. They are not looking to be authoritative on anything. They're there for their members. It has been something that has evolved into usage, but that's why we stood up the ISO Geodetic Registry as the official registry for these types of data sets. So again, there I would encourage nations to participate in Advisory Group 12 to make sure that your information is loaded up correctly so that it's available for pull from GIS databases and programmers. And then we've seen this slide before, but I'll bring it back to home just to talk about all the different vertical surface relationships. All of this is about trying to bring things in and integrate it so that when we talk about chart depths to heights on land to trying to deal with how we get from one to the other, I want it all in a consistent reference frame, one that can be moved between, that provides consistent coordinates for everyone. Thank you for your attention.
Thank you, Dan. Thank you, Dan. We'll take the Q&A at the end of the session. Now we invite Pak Arif, who is presenting the National Regulations for Integration of Land and Sea, the case of Indonesia. And maybe this answers Victor's question, why is Bathy and Topo? They have more water than land. Pak Arif.
Thank you, Pak Berry. So, good morning, ladies and gentlemen. At this moment, I will discuss about the policies regarding the geospatial information, or specifically integration land and sea in Indonesia. So I will be talking about some background and then agencies of integrating land and sea, and then policy and regulation on integrating land and sea, challenges and closing remarks. So as you know that Indonesia is an archipelagic state with more than 17,000 islands. So when you need to integrate the whole country, and it comes to a challenge, big challenge, especially in the vertical reference system. So as many speakers mentioned about this, that we face a lot of problem especially in coastal area, where integration of land and sea geospatial data is very important to overcome the problem holistically. So there is no way. So this is a case in Indonesia. We have so many problems, especially with the land or inundated or tidal flood in the land. Also tsunami. This is an example of how the tidal flood affected the Indonesian area. You already see maybe the left image, but on the right image, you see that within the last 10 years, the coastline has been changed in some area up to 3 kilometers after 3 years. So this is caused not only by sea level rise. Sea level rise relatively small because it's about maybe 5 or 6 millimeter per year, but the land subsidence is very high. It's in some area 10, like in this Semarang, it could be 15 centimeters per year. So if within the last 10 years, it's already 1.5 meter subsidence. So fortunately, we have some regulation regarding the geospatial information. We have law number 4, year 2011. This is regarding the geospatial information, and this is the highest regulation about the geospatial information in Indonesia. Previously, in this law, we have 3 types of base map. One for land, for coastal, and for sea or marine. But in 2023, there is amendment by Omnibus Law. So this Omnibus Law actually revised more than 75 law at once, and our law also has been revised. So in this law, the base map is only one type, which is Indonesian topographic base map. It's called Peta Rupa Bumi Indonesia. Rupa Bumi means topographic. And this base map integrates the geospatial information on land and sea, including the coastal. So we also have several operational regulation based on this law. This is another operational regulation, more detailed. So here we already mentioned that the Geoid is the vertical reference for our base map. We also have mandated to implement the one map policy in Indonesia, and in this mandate that the implementation of the one map policy should use geodetic control network and also base map to as a single reference for creating any geospatial information. So Pak Anton is actually who leads this program. This is we also have a regulation regarding the special reference, specifically. So in this, I will only mention the vertical one because this is the most important regulation for vertical reference for integrating land and sea. So we identify 3 vertical reference systems in Indonesia. One is a Geoid or Geoid undulation. This is a vertical distance from the Geoid perpendicular to the reference ellipsoid surface. This is a reference for the automatic height. And then we use also a tidal datum. We define only 5 tidal datum: highest astronomical tide, mean high water spring, mean sea level, mean lower water spring, and also lowest astronomical tide. So this is a vertical reference of local height and particularly used by specific application such as navigation. Sea navigation, we use the lowest astronomical tide. And then the third one is reference ellipsoid. Of course, you know all of this. This is a reference for geodetic height. When we measure using the GNSS, we will get this ellipsoidal height or geodetic height. So, where are these vertical reference system meet? So we have about 200. We operate 293 tidal stations, and each of these tidal stations has a benchmark, permanent point, and we measure this benchmark by 3 observations. Of course, we tie the tidal observation to this benchmark using the level measurement, and then also we measure the GNSS observation. We also measure the gravity observation. So these points or benchmark are used as a tie point to make the tidal datum model and also the Geoid for the whole country. So at this point, we know the relationship between Geoid, tidal datum, those 5 tidal datum, also the reference ellipsoid. So this is what I mentioned before, that before the amendment of law for year 2011, we have 3 types of basemaps, each for land, coastal, and also marine or sea. And each of these basemap has different specification, especially on the vertical reference system. For example, in the land basemap, we use mean sea level. In the coastal, we use low astronomical tide, and for the sea, we use also low astronomical tide for the depth, but mean sea level for the height in the land or the elevation, land elevation. So after the amendment, we only have one type of basemap, which is called Peta Rupa Bumi, or Indonesian topographic basemap, and this basemap integrates the reference system. We use Geoid as the vertical reference system. We define 3 types of, well, we call it coastlines, which is mean high water spring, mean sea level, and lowest astronomical tide. Why we identify these 3? Because a lot of many users also require these 3 coastline for their own purpose. So since we provide the basemap for national use, we provide this information for them. So this is the challenges when we integrating the geospatial information and land and sea in Indonesia especially. So this is the most data that has been used by many users for land and sea. Indonesian topographic basemap or Peta Rupa Bumi Indonesia, and also nautical chart published by the Hydrographic Office or Center for Hydro-Oceanographic of the Navy. So this is the official hydrographic office in Indonesia. We use different reference system here, different specification. For example, for the horizontal reference system, a little bit different, of course. We use our national reference system, while the nautical chart use the global reference system, which is WGS84. For the vertical reference system, for the topographic basemap, we use Geoid, or what we call is Indonesian Geoid 2020. That's the first Geoid we have for the whole country, and defined in 2020. While the nautical chart use lowest astronomical tide for depth reference and mean sea level for height or land elevation. The projection system, topographic basemap use transverse Mercator, while the nautical chart use Mercator. Grid system is different also, and the use of this map also different. So the base map mainly used as national base map for land and marine application, or application that requires integration of land and sea. So, and while the nautical chart mainly used for navigation or application that do not require integration of land and sea. So integration of these 2 kind of base map is challenging. We cannot integrate the map, the final product. We have, if you want to integrate these 2 information, we have to go back to the data, the geospatial data, which is the bathymetric data and elevation data, and integrate the vertical reference first. Then we create the product, another product based on the specification. But we cannot push the nautical chart to use the land or topographic base map specification, because they need to use it for safe navigation, which is we need LAT, or the lowest the lowest tidal level for safe navigation. While we don't need this for the land, but we need the integration, the seamless model for land and sea. So Another challenge is that different application requires different vertical reference system. So a single reference system is required for application that needs it to integrate land and sea geospatial data. For example, integrated coastal management, of course, we need to integrate the data, disaster risk management, sea level and land subsidence monitoring. We have to use the same vertical reference here. Environmental monitoring, conservation, also infrastructure development. But some application maybe do not require integration of land and sea, such as marine navigation. We don't need to integrate the land and sea because the ship will not go to the land, right? So ship only find the safest waterway to sail. Or fisheries management, marine habitat conservation, we don't need to integrate this because only focus on the marine. So we have to consider this. We don't have to push them to integrate. But when we need to integrate the data between land and sea, what is the specification to integrate? This is what we have to agree, I think. So in our case, regardless of the vertical reference system used by an application, its geospatial data must be able to be integrated into a single vertical reference system. Okay, we have topographic base map, we have nautical chart, but these two maps comes from the data acquisition. So it is better to keep this to maintain this, and if we need to integrate these two data, then we need to integrate first the vertical reference system. I think that's more easy, I think, rather than we integrate the map, the final product. So this is, in our case, the integration of land and sea requires a single reference system for land and sea, either horizontal or vertical. So for horizontal, in Indonesia, we use the Indonesian Geospatial Reference System 2013. We have updated the epoch to 1st of January 2021. This is also based on ITRF 2014. I think in the next few years, we will also update to the ITRF 2020. And vertical system, or unified vertical system for the whole country of Indonesia, we use Geoid. And also important, I think, to use the same standard for the future. For example, like coastline. Coastline, what coastline do you define? In our Indonesian case, we only define 3 types of coastline: mean high water spring, mean sea level, and also lowest astronomical tide. Also the contours for height and depth, land elevation and depth, we also to define the same attribute or the same definition. This is our workflow to integrate the data. So we use different technology, different method to capture the data on land, on marine, also on intertidal area. So for land area, so we have a program to accelerate the provision of national base map, large scale, within the next 5 years. But the president requests us to complete within the 3 years. So it's, yeah, we try to do that. So in land area, we use mainly, because this is regarding the acceleration, only 3 or maximum 5 years, we use aerial photogrammetry and LiDAR for urban area. But for rural and forest area, we use airborne SAR, airborne interferometric synthetic aperture radar. Why we choose radar? Because this is the only technology that can be used in Indonesia within short time. And also the price is much cheaper than the aerial photo. The cost is about 1 to 10, I think, 10%. And we can complete the whole area of Indonesia within the acquisition, within 2 or 3 years maximum. And the problem why we use the radar is, as you know, in Bogor we experience raining every day, and almost the whole country of Indonesia experience the same thing. So that's why we choose radar, because radar can penetrate the clouds. We can do the survey at daytime or nighttime. Even when it is raining, we still can do the data acquisition. So that's why it's very effective and efficient. And for intertidal area, we use several methods. We use UFO mapping. We use a satellite-derived bathymetry, especially at clear water and shallow. We use also USV, unmanned surface vehicle, for the shallow water that the survey boat cannot go there. So if we are lucky, we have clear, we use also LiDAR bathymetry. But this LiDAR bathymetry only applicable in the eastern part of Indonesia. And then for marine, we use sounding, either multi-beam echo sounding or single beam echo sounding. So from this method, we only get 3 types of output: the ortho image, either from aerial photo, from radar, and also the DSM and DTM, digital surface model and digital terrain model. So once we get this, since we use the same, during the acquisition or the processing, maybe we use different reference system, especially for the vertical. But at the end, we will integrate this data into one single reference system, especially for the vertical one. So you know, when we are doing the echo sounding, for example, we use the tidal datum, and we have to convert it to Geoid later. When using the GPS or GNSS, we use ellipsoid reference for the vertical reference. So once we got these 3 aerial orthorectified image, DSM and DTM, then we create the base map and also the DEM for land and sea seamlessly. Then we do the next production level, publication and dissemination, also for use in many GIS applications. So this is an example of how we integrate land and sea in Kendari, the capital city of Southeast Sulawesi. This is newly created this year. So for the closing, 2 seconds. So fortunately, Indonesia has adequate policies and regulation for land and sea integration. And BIG is mandated by regulation to provide geodetic control network and also base map as a single reference in Indonesia. And the use of single reference is the key to integrate land and sea geospatial data. So whatever the reference or specification used by the producer, we have to be able to integrate into one vertical reference system. So this is the reference system used for national use in Indonesia. Horizontal system, we use Indonesian Geospatial Reference System 2013. Unified vertical reference system, we use Indonesian Geoid 2020. Tidal datum, we have 5. And the coastline, we define 3 types of coastline. But what we have to mention here is that different geospatial reference system may be used for specific application, such as marine navigation that use LAT and MSL for depth and height reference system respectively. So, however, its geospatial data, which is the bathymetric data, should be able to be integrated into a single reference system for use in land and sea integration. So I think that's the point. Thank you very much.
Thank you, Pari. Okay, Let me next introduce Chris Body, but because he's taking the stage the first time, I think you need to know a bit about our friend, Chris Body. Although he sits there quietly, he has done a lot of achievements in his long career. So he's a geospatial standards expert with a wealth of knowledge and experience in developing and promoting standards, not only across the Australian landscape, but also internationally. Okay, I see him a lot of meetings in the OGC as well. And he has been associated with policy development and management of geospatial and imagery standards and related information management in support of the Australian government, spatial policy, agenda and associated infrastructure. His presentation will be Connecting Land and Sea, Federated MSDI Pilot and 19152 Land Administration and Domain Module, which Dan touched on a bit on the Federated Marine Geospatial. So this is a good start to his presentation. Take away, Chris.
Thanks, Barry, and thank you very much for the opportunity to Thanks, Barry, and thanks for the opportunity to Nick and his committee. Thank you very much for the kind invitation. To the hosts and the warm welcome that we've been having, thank you very much. As Perry has indicated, my name is Chris Body. I'm a retired civil servant who's been doing geospatial standards and imagery standards for just on 30 years. So I started as a wee boy down here. So I just want to quickly introduce you to what the Open Geospatial Consortium does. It is, as Dan has indicated, is one of the key standards developing groups that are developing international standards associated with geospatial and imagery, and associated with various other communities that are assisting us in our endeavours to ensure that there is improved interoperability. The members are made up of a number of components or key stakeholders, including commercial, government and research. A lot of OGC work is really done at the research level, and they have made a significant contributions to where we're at the moment. So Dan quickly mentioned how this all works. So if you look at the left-hand side, it is basically, this is where the use cases are starting to thought through, developed, ideas have coming through. Then on the right-hand side is the final product of standards. So like IHO and ISO, the standards is the end product. It is not the driver as such. The use cases are the drivers through to making the standard. Standards reflect on user case and members' requirements. We don't develop standards for the sake of developing the standards. It comes out of you as a community that requires it. It takes some time to going through these use cases, to getting it right. And some of the questions around why does standards take so long to develop is sometimes that you need to thoroughly look through those use cases to ensure that it meets your users' needs and requirements for your outcomes. The development of those standards, or written through, is actually quite quick in terms of the timescales. So, this is how we've started off on our journey through some of this work that we're discussing at the moment. As you can see, we've gone through some pilots and a lot of partnerships to developing where we're at the moment. While you see it is we started in 2015, that was where we really started to understand what our end goal is. Now the end goal is now 9, 10 years down the road and we still haven't got here yet. But during that period of time, our technology has improved significantly and our understanding of what is required from our communities to better manage our systems and our data and our modelling has improved significantly over that journey. And as you can see, we've now starting to look at the land and sea integration. Now, we've been discussing this integration for some period of time, but it's this maturity of thinking at our level has significantly advanced over those years. I'd like to thank the sponsors that have gone through this journey with us. And you can see a number of key ones. Some of them are already in this room. And I'd like to thank those organisations and sponsors for their continuing support through this process. And also, as Dan indicated, the long-term partnership that we have with the 3 specific standards development organisations that has assisted through the last 10 odd years with the partnership of the UN-GGIM, have improved our understanding and to meet the UN-GGIM's programs through our standards bodies development. So why are we doing the Federated Marine Spatial Data Infrastructure pilot? And also, how do we start data integration at the sea and land and sea interface? Many of you in this room indicate that you're doing some of this work, and I bet you it's not easy. And it's not going to get any easier if you don't have a coordinated understanding of improving your interoperability, the standards associated with that, but also internally good governance. Because if you haven't got good governance and policies and the quality of that, then you'll all be asking those sometimes embarrassing questions like, is this authoritative? Can we trust this data? Because when it comes into a critical stage of reporting on an event that happens, can you put your hand on your heart and saying, yes, this is an authoritative, trusted data environment? So, we know that 40% of the world's population live in the coastal zones up to 100 kilometres inland. That is a significant amount. So what's that, 8 billion people that we've got totally? So that's around about 3.5 billion people are associated with or linking that land and sea environment. If we get it wrong, we're going to have a lot of disruptions, annoyed communities. Of that, 75% of those are megacities. And we know how challenging they are at the moment. Also, we've got significant challenges with our climate and impacting where we're at the moment. And at the moment, we've still got significant challenges to address. And unfortunately, it looks like we're still losing the will to turn this curve around. So we'll expect more disasters, more challenges for our communities and governments and our citizens to deal with this. So we've got some big challenges. How do we connect the data and so forth, improve our regional connectivity, but also unlocking the value. So I'm just going to go through 3 test cases that we've been doing over a number of years: Singapore, Canada, and the Caribbean. And I'd like to thank those communities and supporting governments that have provided this information and guidance and leadership around this work. So I'll touch on the first one. So the first one is up the top, is the Singapore Digital Twin and its programs. The second one is down there, the bottom left, is the Digital Arctic. And finally, the Caribbean. So we're looking through what's consistent with these programs and where the data sits and how do we manage and governance this properly. For that to happen, you have to have good standards-based understanding of where all this work is and how does it interlink, and the metadata associated with this and the quality around this. As you can see, there is also a number of companies that are assisting through this process. So the thread is, in Singapore, they gave us an overall scenario, and we've gone through some of the methodologies to bring this together, which we've been discussing over the last day and a half of some of these issues. The Arctic is a bit different in terms of its outcomes and its requirements and its scenarios with the Arctic melt and what's the impact around those parts of the world that are impacted on the climate change and the melt of the Arctic. And the Caribbean, at the equator side, what does that impact on the sea levels and so forth for those communities, and the climate and the weather and hurricanes and so forth, and what does that bring to those communities? So the last part is we're up to phase 5 of how to data integrate the land and sea at its interface. So OGC has had a call out for this phase, and I'm pleased that UK Hydrographic Office and NOAA, thank you, for leading this work. And last week, OGC selected this group of companies to assisting in that program. And I'd like to also thank them for their significant contribution throughout the programs. So you can see they're using best practice, data integration, and web and pilot reporting. And these companies will assist us going forth. And their knowledge is important. So there are two main things the pilot brings to try and understand better what's needed to define best practice on our data and inter-agency interoperability. Because collaboration isn't easy, as we know. It takes time and effort to trust each groups on what we're coming out to. And can existing data sets integrate dramatically? So this is the schedule. The green has already been indicated. And you can see it is a fairly short timeline that we're trying to achieve for this particular part of the phase. And the one in bold, I believe may be shown at the March OGC meeting. And I think it's going to be in Europe somewhere. It hasn't been determined yet. So that's the OGC side of things, but I just wanted to introduce the land administration domain model that fundamentally provides some other information modelling around land administration and how some of this work starts to integrate with the land and sea. Part 1 and 3 have already been published. 2, 4 and 5 are in their final stage and will be published early next year as an international standard. And Part 6, through the implementations, OGC will be leading that for use cases. And if you have got use cases, which we have in this room, I applaud you to approach OGC around some of this work. One of the reasons why we had to do, well, updated 19152, as you can see from this photo that's in Delft in the Netherlands, is how do we look at rights restrictions for land ownership when you've got this type of example. And it's about 3D, 4D environments. So in summary, OGC, ISO TC211 and FIG are ongoing programs for the standards development of supporting our community here. The key deliverable for OGC Land and Sea Pilot is develop a draft best practice document to give you an outline of what we believe is required for good governance and policies associated with this work. The current timeline and funding means that it's only the first step. Your feedback is important for this to continually have ongoing improvements. And I'd like to acknowledge Trevor Taylor for doing project leading this project, and his email address is at the bottom. So thank you very much for your attention, and I wish the rest of the week is as successful as the last day and a half. So thank you very much.
Thank you, Chris. Okay, next while they prepare for our online presentation. Oh, I see it's that okay sign there. Let me introduce Ilaria Tani. She is a distinguished expert in the field of international maritime law, currently serving as an adjunct professor at the University of Milan. Don't make me read out in Italian, I'm not good at it. Where she teaches courses on international law of the sea and ocean affairs, law and policy. Okay, and her presentation today is Joining Land and Sea, Implications under the Law of the Sea Perspective. I'm quite mindful of the time, now it's 12:05, so if I can request Ilaria to keep it within 15 minutes so that we at least have some time for Q&A. Is she online? Yes. Over to you, Ilan.
Yes, I am online. Good morning, everyone. I'm trying to share my presentation, but it doesn't seem to work. So I would kindly ask.
Sorry, Laura, just hold. Okay. Good morning.
Good morning. Can you hear me? Buongiorno. Can you hear me? Yes. So I'm trying to share my presentation, but apparently it doesn't allow me to do it. So if someone can do it for me, I will. You should have my presentation in the files. Oh, thank you very much. I can see it. Okay, great. So I will ask you to move ahead while I speak. So good morning again, everyone. Let me thank the UN Global Geodetic Center of Excellence for the kind invitation and the Geospatial Information Agency of Indonesia for organizing and hosting the workshop. And thank you also for considering a legal contribution in our agenda. So if you can move to the next slide, to the first slide, please. Thank you. So as a member of the Marine Working Group and the Policy and Legal Frameworks Working Group of UN-GGIM, I would start by emphasizing...
Ilaria, can you just hold
yes?
on? Your slides are not being presented. Do you want us to present the slides up here?
Yes, thank you. Can you do that?
Yeah.
I thought you were seeing the slide.
I think they have your slides. Can you just maybe give us a couple of minutes to get your slides out?
Sure. Yes, sure.
Okay. Okay, Lara, off you go.
Okay, thank you. So I would emphasize the importance of the law-science interface, which is especially relevant in a dialogue on the land-sea interface and in discussions such as those addressing the consequences of sea level rise. The concept note of our workshop puts great emphasis on the issue of sea level rise, so I would like to focus on that. An issue that does not find any mention, of course, in the United Nations Convention on the Law of the Sea, because it was negotiated at a time when climate change was not yet a concern. Next slide, please. So sea level rise raises complex legal questions, not only of geospatial nature. As a matter of fact, the complexity and the significance of the impacts of sea level rise are evidenced by the increasing attention devoted to the topic within the General Assembly, the Security Council, and various other UN bodies. Next slide, please. There are international and regional courts and tribunals that address the matter in the context of advisory opinions relating to climate change, in particular the International American Court of Human Rights, the International Tribunal for the Law of the Sea, and the International Court of Justice. Next, please. So due to the complexity of the legal issues that sea level rise raises, since 2019, the topic has been included in the program of work of the International Law Commission. The International Law Commission is the subsidiary body of the General Assembly that was established in 1947 to perform the mandate of the General Assembly to initiate studies and make recommendations for the purpose of encouraging the progressive development of international law and its codification. And in 2019, the ILC, the International Law Commission, included sea level rise in its program of work and decided to establish an open-ended study group on the topic. The work of this group was further developed on the basis of a number of submissions to the ILC by the member states and through national statements presented before the Sixth Committee of the General Assembly, which is the primary forum for the consideration of legal questions within the United Nations. Next, please. The first issue paper of the ILC, of the International Law Commission, on the topic of sea level rise in relation to international law was circulated to the UN member states in 2020, and in 2023 the co-chairs of the study group circulated an additional paper addressing specific geospatial issues that are of utmost relevance to our workshop. So I will return to these recent developments after having quickly recalled some of the relevant provisions of UNCLOS, of the United Nations Convention on the Law of the Sea, which clearly demonstrate the importance of the law-science interface in our discussion on the land-sea interface. Next, please. As a matter of fact, the maximum extent of all national maritime spaces is established by law in terms of a fixed number of nautical miles. This maximum extent is measured from a baseline, which is determined by legal rules, but measured through science and expressed in geospatial terms. So UNCLOS, the Convention on the Law of the Sea, in Article 5, identifies the normal baseline with the low water mark along the coast as marked on large-scale charts officially recognized by the coastal state. Charts that do not have to be produced by the same coastal state, but also by foreign hydrographic services if needed, and this is indeed the practice of many states. Next, please. When a state uses the normal baseline under Article 5 of the Convention, it is not under the obligation of due publicity through the deposit of the charts or the geographical coordinates with the UN Secretary General, as it would be should it adopt another method. You see that Article 16 of the Convention on the obligation of due publicity does not mention Article 5. It mentions Article 7, Article 9, Article 10, other methods to draw baselines. Next, please. The low water mark is called normal baseline because it makes the legal boundary between land and sea coincide with that same line that in nature distinguishes the two elements. The normal baseline represents a criterion for the location of the internal limit of the territorial sea that operates ipso iure, that is to say independently of any expressed declaration or deposit by the coastal state. This criterion may look simple to a lawyer, as it corresponds to the natural boundary between land and sea, but we know that it may present significant challenges from both hydrographic and cartographic perspectives due to the lack of a uniform determination of the low water line around the world and the use of different criteria such as the average of all low waters, the average of spring tides, and so on. Next, please. So during the third conference on the law of the sea in the 70s, when UNCLOS, when the convention was being negotiated, interventions on cartographic techniques were rare, although some, like the one that we can see here of the delegate from Yemen, hoped that states would agree on uniform criteria. However, this hope was not followed up. The existence of different methods around the world to identify the natural divide between land and sea under the Convention explains why Article 5 requires that the low water line be indicated on nautical charts that have been officially recognized by the coastal state. Next, please. So from a legal perspective, the purpose is not only to inform navigators of the low tide limit for their safety, but also to identify among the various available cartographic representations which one is to be used in international relations, should any dispute arise. Each state is also free to use the scale it deems preferable to indicate the low water line, provided that, according to Article 5, it is a large-scale chart, because on charts of small or intermediate scales, the low water line is not always discernible as a separate line distinct from the high water line. This is said by also the Secretariat. In this regard, the UN Secretary General provides clarifications, as does the IHO, the International Hydrographic Organization, although it is still a fact that in some regions of the world, only small-scale charts are available. Next, please. So addressing the issue in the arbitration of 2016 concerning the South China Sea in the case of Philippines versus China, the arbitral tribunal noted that only a few of the nautical charts in the record are large-scale. The tribunal identified some relevant evidence in nautical charts up to 1 to 250,000 scale. Beyond this, however, the tribunal does not consider that small-scale charts offer meaningful evidence. So precise geospatial information is crucial in judicial and arbitral proceedings. Next, please. The use of the normal baseline is contrasted with non-normal or artificial baselines on the right, which are such because they move away from the natural boundary between land and sea. These are straight lines that geometrically no longer separate the land from the sea, but the sea from the sea, because they run across the water, connecting base points located on land and determined by the coastal state. The use of straight baselines obviously results in a seaward expansion of the maritime zones of the coastal state, causing a shift seaward from the normal baseline. This shift causes a corresponding reduction of the high seas, where all states enjoy certain freedoms according to the Convention on the Law of the Sea. So, next slide, please. The legal question here lies in identifying the cases where international law permits the coastal state to deviate from the normal baseline rule to benefit from the system of straight baselines. Article 7 of the Convention on the Law of the Sea has a complex structure because it attempts to provide solutions to this problem. From a geospatial and a legal point of view, the identification of the relevant base points along the coast is crucial. From a legal perspective, there is therefore this dualism between normal and artificial baseline systems, and it is up to the coastal state to decide which one to use, provided that it complies with the Convention. States around the world have adopted different systems of baselines, also mixing the two kinds, like Italy you see in the picture, adopted a mixed system of baselines, the baseline, natural or straight, will always correspond to the internal limit of the territorial sea. Next slide, please. So that said about baselines, in Article 16 of UNCLOS of the Convention on the Law of the Sea concerning the due publicity of straight baselines, we find the obligation to deposit charts or lists of geographical coordinates, but no obligation to update this information. And this leads us to the question of sea level rise. What happens if the relation between land and the sea as represented through the baselines becomes unstable? What happens if the two elements move with respect to a line that was drawn some time ago on a nautical chart, if normal, or deposited with the Secretary General, if artificial, and no longer updated? A typical change occurs when the level of the sea rises and necessarily prompts a reflection on the adjustment of the current internal limit of the territorial sea of states facing the phenomenon. Next, please. The Sea Level Rise Study Group of the ILC, of the International Law Commission, among other relevant areas, focused on the question of legal stability in connection with sea level rise, including the issue of ambulatory versus fixed baselines. It also addressed the potential situation whereby, as a result of sea level rise and the landward shift of the coastline, overlapping areas of the exclusive economic zones of opposite coastal states delimited by a bilateral agreement no longer overlap, or the issue of the consequences of the situation whereby an agreed land boundary terminus ends up being located out at sea because of sea level rise. Next, please. So after the issuance of the first issue paper by the ILC study group in 2020 and the debate on it in the Commission in 2021, we know that some states have taken collective action. The most notable was the Declaration on Preserving Maritime Zones in the Face of Climate Change-related Sea Level Rise, issued by the 18 Pacific Islands Forum leaders on 6 August 2021. The declaration contains important references to the legal stability issue in relation to the Convention and sea level rise, for example, in its preamble. The declaration of the heads of state and government of the Alliance of Small Island States, adopted on 22 September 2021, in paragraph 41, makes reference to legal stability, where it affirms the absence of obligation to update baselines information in the UNCLOS, in the Convention, and the opportunity to continue to apply rights and entitlements linked to maritime zones irrespective of their physical change. And further, two organizations endorsed the initiative. Next, please. We can see the Dhaka-Glasgow Declaration of the Climate Vulnerable Forum of 2 November 2021. Next, please. We also have the declaration of the 7th meeting of the Organization of African, Caribbean, and Pacific States Ministers in charge of fisheries and aquaculture of 8 April 2022, which aims at mobilizing resources for adaptation and supports the initiative of the ocean states in freezing the current maritime zones in the face of sea level rise. Next, please. In the light of the submissions of the member states to the International Law Commission Study Group, and in the light of the relevant national statements also made before the 6th Committee of the General Assembly, it is clear that references to the need of legal stability, including the solution of fixed baselines and other limits of maritime zones measured from them, are the most numerous. Numerous are also references to the need to interpret the Convention in such a manner as to respond to the effects of the sea level rise, in the sense that The convention does not forbid the freezing of baselines. The ILC study group noted that these are the issues considered as the most relevant to the aspects of the law of the sea related to sea level rise. And furthermore, no states have so far contested the option of fixed baselines, even those that have national legislation providing for ambulatory baselines. Next, please. Also, in relation to sea level rise and maritime boundaries, a preliminary observation of the ILC study group lies in the importance to ensure the continuity of pre-existing boundaries in the interest of stability and the prevention of conflicts. So these are just some of the legal questions addressed by the International Law Commission on the issue of sea level rise in relation to international law. There are many others. Next, please. In 2025, the ILC study group will seek to finalize a substantive report on the topic as a whole by consolidating the results of the work undertaken so far, including also questions related to statehood, the preservation of the territorial integrity of states, and the protection of persons affected by sea level rise. So evidently our work on this matter is timely, is in line with the utmost interest of the member states through their legal experts within the General Assembly, as demonstrated by the substantive matters discussed within the 6th Committee of the General Assembly and studied by the International Law Commission. Thank you very much for your attention.
Thank you, Hilaria. Sorry, but can you just stay on the line? Or maybe you'd like to have a cup of coffee to stay awake? Anyway.
Okay, thank you very much.
Yeah. Before I open up the floor for Q&A, maybe can I just do a summary what I feel has been the key points. One, I'd like the statement, I think, in Chris' presentation. It says committed and strong community, okay? And there are two parts to this. If you look at it, you look at the technical, and I think now you look at Hilaria's presentation, we have the law on our side as well. This is a good justification. And one of the things which came up first is from Pak Arif and from many other presentations yesterday as well, is on a single reference frame. There's a need for standards. But the single reference frame can be both horizontal as well as vertical, but vertical seems to be the more urgent and important domain in which we need to look at. And it seems as though besides your datums, one of the things which keeps coming up is using gravity, the mean sea level, as one of the means to measure tidal levels as well. Because otherwise we have, like you suggested, different users, you have mean sea level, you have LAT and all the different levels. It's a confusion. But I think if you want to present a case, you make a case to the decision makers, something which is understandable on a global basis. But how do you do this? And that's where we talk about standards. And last but not least, I feel that if you look at the presentation, whether it's from the OGC, and you look at the participants in this room, it's multi-sectoral. Private and public sectors, research institutions, industry as well. It's collaboration, and coming back, we need a committed and strong community in which we can have one single vision. And we need to drive that. But we, as a governing bodies of standards, we need to make sure that that is done, that is clear to everybody. And that's the agreed standards where everybody will abide to. Okay, the floor is open. Any questions? Except for the Hilaria, because unfortunately her presentation was only not shared with you earlier, but I'm sure she will share an email if you have other questions, because quite interesting if you actually link it to the law of the sea. and the more recent one for the smaller states regarding ensuring that the baselines don't change despite of climate change. Okay? Any takers? I know you are waiting. I've been given the authority to extend the discussion by whatever time I need, maybe an hour. No? Yes, Nick?
Thank you, Mr. Chair, and thank you to our speakers. I've got a question for Ilaria. I hope you can hear me online.
Yes, of course.
Yeah. Okay,
yes,
great.
I can hear you.
It's Nick Brown here. I was just curious. I'm hesitant to offer, but I feel like at the moment there is a bit of a disconnect between what's happening with particularly the work you're doing on the legal side and how many geodetic or geospatial people are involved in these working groups and discussions. Do you think that there is, from the legal aspect, you could do with more support from the geospatial and geodetic community in these discussions, or do you think there's enough support in there already?
Thank you very much, Nick, for the question. Actually, there is some link between the two worlds. I'm very lucky to be a member of the Marine Working Group and the Policy and Legal Working Group. I come from the law of the sea world, so I'm not that used to other issues related to land administration and other issues that are taken up by other working groups of UN-GGIM. But I see that some improvements can be highlighted. For example, the General Assembly of the United Nations at the end of 2022 requested the Secretary General to produce a publication on marine geospatial data management, and that publication was issued this year, and it is accessible online. And I think this is a very important example of how the legal world and the geospatial world can work together. The example of the International Law Commission's study on sea level rise is another example, because the study group is open to contributions from member states, and of course contributions can also come from groups of mixed groups of experts from the legal side and from the geospatial side. I think that a lot of work still has to be done, but it is very important to in my opinion, it's very important that the work that we are doing. So I hope that we will continue in this regard. I would like to share with you, of course, the publication of the Secretariat on Marine Geospatial Information Management, because it is an example of a publication produced by a legal division, the Division for Ocean Affairs and the Law of the Sea, which is a division within the Office of Legal Affairs of the United Nations, that discusses the geospatial information management, thanks to the contribution of member states and relevant international organizations.
Thank you, Lara. Any other questions? Don't get intimidated by the lawyers. No? Oh, Chris?
I've got a question for everyone then. How much of your member states, companies, agencies are really engaging in the standards development groups? And if you are, that's good, but if you aren't or need assistance, please approach myself or Trevor or even Nick to assisting in some of your programs that you want to get through the standards development organisations. Utilise this community for some of your outcomes that you are starting to be challenged on, but also Nick has some of the authority to moving this through the organisation as such to improve our information flow and integration of this land and the sea programs, because it is important that we start utilising the organisations that will assist our outcomes. So that's advertising, I suppose. Thanks.
Thanks, Chris. Because I actually have a question for Dan, because in his presentation he actually showed TC211, and if you look at the TC211 ISO, there's a lot of committees, but which one do you select and which one should we be in? It would make a difference. I think that's something which a lot of countries are not aware of, the ISO framework or which committee.
So I would point out that being in TC211, if you're assigned as a member, certainly I participate in Advisory Group 12, but because I am also I participate in any of the working groups I can choose to. And really what it comes down to is which standards that are pertinent to your country. So 19111 came up for review. That one's pretty basic and should be of interest to everyone. So, but by being a member of some part of the TC211, then you have the ability to participate in the different working groups. And a lot of times it's just being engaged. I would say working group, it depends on the working groups, but 9's been very active, working group 1 as well. But you can go through and you can see which standards are the most pertinent ones to you, and you can see which working groups have those responsibilities. In my presentation, the links are live. You can go to the TC211 page where it lists all the different standards, and you can actually see which ones fall under the purview of the different working groups. And I encourage you to participate in those working groups, but in any other standards that might come up for review.
Good, Dan, but for a follow-up question, actually one of your slides actually frightens me. Is ITRS versus WGS 84. That day is coming very soon. When is that day?
Harbinger doom. I would say that the issue for me is I keep seeing a lot about autonomous vehicles on sea, on land, and in the air. And that's where the integration piece starts to become much more critical. Is if you really want to be moving autonomously, you can't be, I mean, when they talk about WGS 84, they're saying, oh, it's identical. Yep, a 95% confidence level at, plus minus a meter confidence interval. So if you're good at plus minus meter level, then that's fine. And again, if you're out in the middle of the ocean, you're probably only interested in your horizontal coordinates. But once you start to get concerned about your vertical coordinates, that's when you need to worry about switching. And that's starting to come into play. The Baltic Sea, there was a movement to adopt the Geoid as a basis for vertical control. That's what we're going to be implementing in the U.S. for the U.S. territorial waters. There are a lot of other countries that are moving in that same direction. So the soon is coming for us in the next couple of years. We're going to be implementing a Geoid-based vertical datum, and I need to have the level of precision and accuracy to be there.
So there's another justification to the decision makers why we need to collaborate and set the standards, right? Well, but Arif, in your presentation, a lot of the coastline in Indonesia is actually subsiding as we see. Which government authorities are using information to to protect your shorelines further? Because you have a long coastline.
Yes, to protect the coastline, actually, responsibility of the regional government. So they may say recover or either build. If the project is big, like building the giant wall to protect the coastline, then the central government may involve. But the main responsibility is on the regional government. So what the BIG did is we provide the information on the subsidence rate to monitor the land subsidence. We have a national working group to deal with this, It is led by, it's already dismissed the minister, the coordinating minister of for Maritime and Infestation, but it's not exist anymore. But one of the tasks of for BIG is actually to monitor using the oil station, core station, also tide station, also using the SAR data to monitor.
Thank you, Parif. Any questions from the floor? It's very silent audience suddenly. Okay, I shall not take too much of your time unless there is. Richard?
Yes, I've got a question about, it's probably more for Dan, this distinction between WGS84 and ITRS or ITRF for coastal navigation or harbour navigation. Is there some discussion about what standard there might be for reporting of epochs and transformations? Because a lot of the vessels will use a PPP type positioning, and when you're in the close harbour area, you know, that needs to relate to the charting in that immediate vicinity. Is there a sort of a move to standardise that?
I think that's what we're trying to get to, is that for the autonomous shipping coming in, that's when they're going to be, you've got the ECDIS, you've got the chart, it's all electronic, but the positioning of the ship then within the system is critical. And one of the things we're going to be looking to is the use of coastal navigation in terms of augmentation systems from onshore, ground-based augmentation. Right now, when we do charting, we have an elliptically referenced tidal datum. So the shipping comes in, figures out where it is in a GNSS and a geometric frame, and then applies transformations to map out the bottom. Once you've mapped that out, then it becomes the operators. They're coming in, and you want to make sure they're in a consistent system as you've just mapped the bottom out, and as you mapped out all of the positions on land and the built infrastructure. So we're trying to get that to be consistent. You know, the complaint about the WGS84 is you can make a measurement today, you can say that's your charted depth of the height of the bridge, but because it's a dynamic reference system with no memory, if you will, that there's no consistency, there's no deformation model, you don't know that when you come back in the future that that value is still valid. This is where you have to have the terrestrial reference system, something that can either be static and that you can measure the change in, or something that has a modeled amount of change that you can still look for any further change in. But if you don't have that, then you don't necessarily have the high confidence that you're passing through. And again, as I emphasized for Perry's question, it's the precision and accuracy when you want to be moving autonomously. And the idea then is that you're going to need some type of augmentation system to bring the ships in to get them onto the terrestrial system as they're coming into the shallow waters and into the coastal navigation component. So I'm not sure if I answered your question.
If there are more follow-up questions, Richard, it's over lunch. Okay, one of the areas we have not touched on is capacity building, which I hope in the subsequent sessions you'll have the opportunity. But if not, we thank Alaria for waking up so early to join us. Okay, and I'm sure you can't go back to sleep, so you have to prepare to go back to work. Anyway, we will enjoy our lunch, you enjoy your breakfast. Okay, thank you everybody. Now to the MC.
Thank you very much to our moderator and speakers for sharing such insightful information. But before we end this session, with all due respect, Dr. Oy, I'd like you to deliver the token of appreciation to all our speakers. My apologies to Mr. Dan Roman. There is no second souvenir for you since you've already received one. But please still join the group photo. Mrs. Tani, can you please join us for the group photo? So basically you are on the screen right now. Just give your best of smile.
Great.
Okay. Okay, let's have a group photo session in 1, 2, and 3. Once more. 1, 2, 3. Thank you. Please give a big round of applause for all of us. Okay. Distinguished guests, ladies and gentlemen, we have reached the lunch break. This is the perfect time to relax, enjoy the meal, and recharge before we continue with the next session. You are invited to have lunch at Meranti Restaurant, the same venue as breakfast. And for Muslim participants, the prayer room is located at second floor near the kids area. And I have an added information for you. If anyone is feeling unwell today, kindly approach the registration desk and please let us know. Please note that all participants, we would really appreciate if you could go back to this meeting room before 2 p.m. so we can start the next session on time. Ladies and gentlemen, enjoy your lunch. Thank you.
Fly me to the moon and let me play among the stars. Let me see what spring is like on Jupiter and Mars. In other words, hold my hand. In other words, baby, kiss me. Fill my heart with song and let me sing forevermore. You are all I long for.
Ladies and gentlemen, I know this is unplanned, but please join the group photo session if you want. Please, all of you, all the guests and participants, come join the group photo session. Can I also join too? Ladies and gentlemen, we request all of you back to your seats because the next agenda will begin in a short while. May we kindly ask you to be seated? Thank you. Ladies and gentlemen, for those of you who are still outside the room, may we kindly ask you to have a seat. Thank you. Ladies and gentlemen, the event will begin in 1 minute. I kindly request you to be back to your seat. Distinguished guests, ladies and gentlemen, now we have come to our next agenda, the 7th session, Geoid and Sea Level Modeling. This session will be moderated by Mr. Hafid, the Director of Boundary Mapping and Geographical Names of BIG. With a 20-year career at BIG, he has held key leadership roles, including Head of Gravity and Tidal Field Division, Land and Sea Boundary Mapping Division, and Regional and National Boundary Mapping Centers. He later led the Center for Marine and Coastal Environmental Mapping and the Center for Management and Dissemination of Geographical Information. Currently, he serves as Director of Boundary Mapping and Geographical Names. Without further ado, welcome our moderator, Mr. Hafid. Please give a big round of applause.
Thank you very much. Good afternoon, ladies and gentlemen. I hope you all had a delicious lunch and that your energy is fully recharged. Is it okay with the lunch? Now that our body batteries are full, let's make sure none of us accidentally switch to sleep mode during this session, because it's already 7 sessions. The 7 sessions, we talk about geoid, we talk about chart datum, ellipsoidal height, and so on and so on. Okay, we will continue our discussing now how geoid and sea level modeling can join land and the sea. And of course, this interesting session, the theme of this 7 session highlights a crucial and exciting challenge in the creating geoid and sea level modeling to create a seamless connection between land and sea. This integration has significant implication not only for the scientific community, but also for policymakers, urban planners, and industries that rely on accurate geospatial data for decision making. Without further ado, let us welcome our esteemed speakers for this session. I invite to join me in on the stage, Dr. Anna Riedel. Dr. Anna Riedel is a University of Tasmania alumni, graduating with a Bachelor of Surveying and Spatial Science honors in 2011, and started at Geoscience Australia in 2012 as a graduate geodesist, where she enjoyed understanding the movement of the Earth as it changed size and shape in response to the distribution of mass within and upon its surface. Dr. Riedel completed her PhD in Geometric Engineering Geodesy in 2021, looking at the crustal deformation of the Australian continent. And the second speaker for this session, I invite Pak Dudi Darmawan Wijaya. Please join with us. Dr. Technical Dudi Darmawan Wijaya is a prominent academic in the field of geodesy, serving as faculty member at the Institut Teknologi Bandung, ITB. His expertise spans geodesy, geometric, and hydrography, with a focus on the application of satellite-based technologies for environmental and geospatial analysis. Okay, and the third speaker, I invite Masano Sumiyoshi. Please join with us. Mr. Masano Sumiyoshi began his career in geohydrography in 2013 at the Hydrographic and Oceanographic Department, Japan Coast Guard. He has spent more than 10 years at the Japan Coast Guard, focusing on research and technology development in hydrographic surveys. And the last but not least, I invite Pak Wiwin Windu Pranata. Dr. Rernat Wiwin Windu Pranata is a prominent academic and researcher at the Institut Teknologi Bandung, ITB, specifically in the Geodesy and Geomatics Engineering Department. His educational background includes bachelor degree in Geodetic Engineering from ITB, master's degree in Physical Oceanography and Atmospheric Science from ITB, doctorate in Coastal Geoscience Engineering from Kiel University, Germany. His research focus on marine research modeling and disaster mitigation. For the first speaker, Dr. Anna Riedel, the floor is yours. Please, take your time.
Well, thank you very much to everybody for coming to the dreaded after-lunch session. It is my absolute pleasure to be here with you today, and I'd like to thank the GGCE and BIG for co-organising this workshop. It's an honour to be part of the first workshop that the GGCE have planned. All right, today I'd like to take you through some of the examples in an Australian context of the Geoid models that we have operationally available today. To start with, I'd like to just briefly introduce you to Positioning Australia and to let you know that this isn't just my work alone. This is representing the work of an absolute cohort of people across the country, not only from Geoscience Australia, but also across our state and territory jurisdictions, the Hydrographic Office, and also our academic community as well. So Positioning Australia supports the Australian government, industry and research through the definition of an accurate and reliable positioning foundation for location information in Australia and our region. Our role is to use the scientific knowledge, technology and institutional relationships to be the national authority on position verification, lead and strengthen the governance of positioning in Australia through coordinating geodesy and positioning standards, capabilities, advice and information in national and international forums. Lead and coordinate a whole of government position, navigation and timing capability that is well integrated with and supportive of the whole of the PNT community. And this includes the geospatial industry as well as the stakeholders involved. We look to sustain and improve the Australian Geospatial Reference System through the operation of our world-class infrastructure and our applied research. And really what I want to say is that the explosion of location-based and precise positioning services is only expected to grow into the future. And this is very much the business case that we've taken to government and saw extra investment built off our foundational geospatial and geodetic capabilities. Talking about the impact of precise positioning has been gold for us at GA. And this really highlights the investment that we've had recently in terms of the impact and the benefit that that brings to everyday Australians. We commissioned a report which investigated the benefits of high accuracy, so we're talking about the 10 centimetre level positioning across Australia and its maritime zones. And what really resonated was that this does improve people's lives. It improves efficiency and productivity. And a great example of that came out of the agricultural sector, where the report found that with access to better positioning services, Australian farmers will be able to develop and adopt future technologies like virtual cattle fencing and precision guidance of their machinery, whether that be the tractors, the harvesters, the trucks, the drones. And it also found that high accuracy positioning will improve the efficient spraying of nutrients, chemicals and water, representing efficiency savings between the 1% and 7%. It might not seem like large numbers, but when you're investing heavily and you're not wanting to expose your waterways to pesticides or herbicides, it really does make a difference on the environmental side as well. And as we heard from Matt earlier, quite a lot of our Australian identity is tied to being a coastal nation. Around 85% of our population lives within 50 kilometres of the coast, and the majority of our national critical infrastructure, whether that be transport, energy, commercial, defence, residential, lies along the coastline and it's vulnerable to climate change, coastal sea level change, and the occurrence of extreme events. And that's to say that, I guess, you're not alone. Everybody is experiencing this and we are feeling it too. And this is where the idea of a physically meaningful height system really comes into play. The vertical datum should be able to guarantee the continuity of heights across national borders, across coastal zones, as well as continuity across the continent and globally. Now, my drawings aren't quite as nice as Nick showed earlier, but we've heard this before. So in Australia, we've gone with two types of height systems, where the geometric part is ignoring Earth's gravity field, it uses straight line paths and it's directly accessible with GNSS. And then the other side, you've got the physical part, which is linked to the Earth's gravity field and measured along a curved plumb line. And I think Nick showed that really neatly earlier. So we're familiar with the concept of gravity and the geoid, but we're seeing a driving need for heights that are physically meaningful. And this is where our geospatial reference system comes into play. So the AGRS is where we have our horizontal datums as well as our vertical datums and the models that connect them. So today we're just going to focus on the vertical component, which are the two that I've highlighted in the box there, which are supported by our Geoid model and our quasi-geoid model. I also like to really highlight that this is probably one of the best simplification diagrams that I've seen of how to describe a reference system, and it's the brainchild of Nick. It comes to you as no surprise. But what we've also done is tried to make it accessible, and that comes with tools and models that are openly available, and one of those is the Geodesy repository, which is online on GitHub as an open source Python repository, which is essentially the codification of our technical manual that contains all of the transformation parameters, the conversion that you need to get between datums or reference systems or the frames. And we use it as a reference standard to help validate and verify where we've got datums and reference systems in place as an authoritative source of information for can you go and check that you've got the right datum in play. If you don't, here's the code to be able to transform between them. And we also have a variety of online tools that are easily accessible as well. So building on Nick's narrative of height is hard, doesn't have to be hard for our users and our stakeholders. And that's very much the philosophy that we've gone with within Australia, is to say, yes, height is hard, but that's why we have technical experts that can do the hard stuff for you and provide you with access to the models and the datums. I'm going to skip a bit of content that I'd planned to prepare because Nick covered that beautifully yesterday about what is a geoid, what is an ellipsoidal height. The Australian height datum is the national legislative datum in Australia, and it will remain so for the near future. And so we need a way to be able to get from GNSS heighting, which is one of the most common technologies used currently for getting height in Australia, to AHD. And to be able to do that, you need a geoid model to be able to connect the ellipsoid to the terrain or to AHD. And that comes with a geometric component, which across Australia varies plus or minus half a metre. And then you have the gravimetric component that forms that Geoid model as well, which can be anywhere from, goodness, minus 30 to plus 80. So there's quite a large variation in the gravimetric component across Australia. And then our alternative working surface to the AHD is we've tagged it with AVWS, or the Australian Vertical Working Surface, which I'll go into a little bit more detail and is supported by a quasi-geoid model as well. So allowing access to a multitude of height systems in Australia which meets users' needs, and it's almost a buyer's choice situation. And so this is Geoid 2020. It is a combined gravimetric and geometric model which supports the conversion of ellipsoidal heights from something like GNSS to our national height datum, being AHD. It has an uncertainty level between 8 to 13 centimetres, and it is only available onshore. It is clipped to the extent of AHD. And so that presents a problem. When we're talking about being able to connect onshore and offshore, how do we deal with that with a datum and a model that is only clipped at the coastline? The data sets that went into it were the beautiful national levelling network that Nick showed, which was over 200,000 kilometres of levelling done in the 70s and future forward. And it's the combination of levelling and gravity data, being the geometric and the gravimetric components. It's made available as a 1 second by 1 second grid. We've got the binary and ASCII files available online, but we also have the tools that allows you just to plug in your height and then get the converted height in AHD. As an alternative, we have the Australian gravimetric quasi-geoid, or AG-QG, which, as you can pretty quickly see, is both onshore and offshore. And so it's an updated version of the gravimetric part of Geoid 2020, but it is a gravimetric only model. It provides the offset between the ellipsoid and the geoid, and it supports direct hiding with GNSS to the vertical working surface without the need to connect to physical survey control marks, which is one of the best benefits that we've been able to communicate about why AVWS might be more suitable than AHD for your application. The uncertainty is also much better, and I'm going to go into that a little bit more in terms that you can get down to an uncertainty of between 1 to 8 centimetres, and that's due to the lack of distortion that's introduced in Geoid 2020, which is part of the levelling components that came from the National Levelling Network. The quasi-geoid, is constructed from a collection of different gravitational data sets from airborne, terrestrial and satellite gravity. And so the main difference between our national datum and the vertical working surface is a combination of the bias and the distortion that is partly due to the ocean's time mean dynamic topography, as well as the short time observation period that the tide gauges were used in terms of the construction of AHD. So there were the 32 tide gauges around the Australian coastline, but only 1 month's worth of data was taken from those to define mean sea level across Australia. And this largely manifests as this north-south tilt that you can see fairly clearly from the model there. And so there still remains quite large areas of uncertainty that we're seeking to improve with the inclusion of new data sets. In terms of the uncertainty maps, this is what they look like. And so AG-QG, as I said, goes for that accuracy at around 1 to 8 centimetres, where the red areas are parts of the country that we're targeting to improve the uncertainty, to drive that down, to provide better access to heights in those areas. What I'd like you to also note here is that the scale bars are quite different. They're almost double in terms of the colour maps, so it can be a little confusing or misconstructed, but essentially it's trying to demonstrate that the AG-QG is much more accurate in terms of the uncertainty they can get out compared to the Geoid 2020. Now I'd like to go into a few examples of how the Geoid models have been applied and are being used in Australia. And I'd like to start with an example from our Victorian government colleagues. What they were able to do was use, as a case study, essentially the quasi-geoid and the vertical working surface as an investment attraction device when they were seeking to get funding from their digital twins model. So the idea that you can create a digital twin is fantastic, but what is it relative to, or what is it referenced to? And they were able to make the argument that having better height in that area is going to only improve your ability to virtually realise a digital representation of whatever you'd like to. So they're going for a full state digital twin, and they were able to get a little bit of investment from their government to fly airborne gravity over eastern Victoria, where this was one of the hotspots of uncertainty in the quasi-geoid. It's quite a mountainous terrain, and so the ability to, well, the business case around flying airborne gravity is far stronger. You're not able to access quite a lot of these locations by foot to do a traditional gravity survey. And I'm very pleased to announce that the survey was completed just a couple of weeks ago. So this is hot off the press, very exciting news. But essentially having better height or the ability to access more precise heights means that you can dive deep into the ability to do scenario planning in your digital twin. It helps you with your mapping in terms of the response and recovery to disasters, which were some of the main business cases that they were able to make. And I'm also very pleased to announce that the code that we're using to update and provide the Geoid models is now also openly available. And so what we're calling the analysis-ready gravity data flow, we'd like to come up with a slightly better name for that. So if you have any ideas, please come and let me know. But that is now openly available as an open source GitHub repository. So please go and take a look. We're inviting people to collaborate, to provide feedback, but essentially this is the code that allows you to ingest gravity data, do the computation, and come out with a geoid at the other end. The initial release is using a tile-based least squares collocation methodology, and it's based off the gravity anomaly observations. So if you're interested, please go and have a look. I won't be able to take questions on the technical components, but I can definitely put you in touch with the team that are responsible for that. Another example that I've got around how AGQG and AVWS are being put to the test is a really nice case study that comes from our Northern Territory colleagues, where they were presented with a challenge to map the intertidal zone of a particularly complicated area in Northern Australia, where the question of native title, of land use planning, boundaries were coming into question. So essentially they were asked to do a survey of the intertidal zone and define where the boundary of that intertidal zone is. And if you've ever done any coastal mapping, you know that that's not an easy feat. This is a very remote area. There's very minimal infrastructure in that area, and so the advice to connect the land component and the sea component was to use the quasi-geoid as the reference surface. So they were taking tide observations from both tide gauges and buoys, and then they were wanting to transfer that height to the onshore survey control. And the quasi-geoid presented essentially the reference frame that enabled that to happen. And so the height transfers were done from the tidal buoys offshore to the onshore survey control marks. And it was a really neat example of where the quasi-geoid and the vertical working surface were able to meet the needs where AHD and AusGeoid 2020 weren't able to perform that. And I'd like to just, I know we've seen a lot of these diagrams, but it's essentially highlighting, this is coming out of our survey, our special publication 9, which is essentially the tides manual for Australia, and it's indicating the reference surfaces and the heights from the hydrographic community. And I think Jen made a really nice point yesterday, which is the language that we use across the communities and across the domains doesn't always gel. And so being able to communicate the intersect between the land and the sea domains is important, and this is potentially one of the diagrams that gets pulled up the most and used to communicate. Well, in Australia, our chart datum is LAT. You've got to relate that to the ellipsoid to be able to get that to an onshore meaningful datum, and the reverse if you're trying to go the other way. And so this leads really neatly into the next example where the Hydrographic Office are working on an AusHydroid model to be able to connect chart datum to the ellipsoid. And so this is AusHydroid, where the quasi-geoid is being considered as one of the gravimetric components to connect land and sea. And this is essentially about showing a correlation between ellipsoidal heights and LAT surfaces. And so it's connecting chart datum to an onshore or onshore datum, essentially. And so in this, the geoid's considered a stationary or a tide-free model, but AusHydroid is reflecting the tidal changes and the deformations as the measurement of water levels at LAT. So it's really demonstrating that people want to be able to connect onshore and offshore data, and the models are being developed. But what we're yet to see is the uncertainty propagation that's coming through this. And so that remains one of the technical challenges that we haven't quite answered yet, but this is all a work in progress. And so the final example that I'd like to go through and to wrap up on today is from our academic community in Australia. So there's seeking proposals for investment in research infrastructure, and the one that they've highlighted and prioritised for the next round of funding is around coastal research infrastructure, indicating that although we have quite a good definition of the coastline, they're wanting to seek more information and asking us as geodetic experts that operate infrastructure in those regions, how do we connect it all together? What is the common reference surface that should be underneath it all? And so this will be, if it is funded, it's currently in the proposal stage, a national scale coastal observing and modelling capability, which is including establishing the relationships with our First Nations colleagues to collect and deliver valuable coastal data. And it's leveraging the existing geodetic investment in coastal infrastructure to be able to build that prototype for the research community. So I'd like to thank you for your time and finish it there. Hopefully I've taken you through a little bit of a walk through what the Geoid models currently are in use in Australia, and also some of the examples of how they've been used. Thank you.
Thank you, Dr. Riddle. It's interesting presentations that Australian gravimetric quasi-geoids with accuracy of 1 to X centimeter, and also Australian geoid 2020 with accuracy of 8 to 13 centimeter. I think ready to join LAM NC combined with our hydroid. Yeah. Okay. We will discuss later about this topic. So the next presentation, the Indonesian Geoid model development, will be presented by Dr. Dudi Darmawanujaya. Please, the stage is yours.
Good afternoon, everybody, and thank you very much for this very nice opportunity for me being here. And before I start my presentation, I just would like to mention a few things. That the first one, this work that I will be presenting in the next few minutes has been being accomplished by our colleagues from BIG, and we are in the university just try to help them to really realize this Indonesian precise Indonesian geoid model to become true. And the second one is, in my presentation, I will be focusing on historical or practical developments of Indonesian geoid models, and I will not talk about what geoid is and how and what for the geoid is, and because this has been presented very nicely by Dr. Anna. And let me start my presentation. Okay, we don't have any version of our Indonesian geoid model. So far, we have only 3 models, and the first one was established back to 1986, where at that time we used very limited gravity data, terrestrial gravity data, and we used all global geoid model, which was GEOS-2, and the accuracy of the first model is, at that time, maybe it was quite okay for meters, but as time goes, we try to also refine the first geoid models, and 10 years later, exactly 10 years later, we had our second geoid models, and there were some improvements where new global geoid model was used, and the terrestrial gravity data a little bit more expanding. And the accuracy is about 1 meter is okay at that time, but since we need more precise geoid models, then BIG tried to establish the latest Indonesian geoid model in 2020, and we call it as INA-GEOID 2020. But among these models, we still do not touch the ocean geoid. So this is one of our challenge, in especially connecting with this this topic, joining land and sea. So I think in the future we need also to consider the ocean geoid model of Indonesian. And in the next my presentation, I will discuss how this ocean geoid will be included in our new plans. Let me briefly mention you the practical development of our current geoid models. For this case, we used only land gravity data, and then thanks to BIG that they have been conducting many gravity surveys, terrestrial gravity survey, absolute gravity survey, and also airborne gravity survey, and all the surveys have covered all the Indonesian land area. So I think this is very good infrastructure that we have so far. And in the development of Geoid 2022, we calculate the raw observation into free air anomaly, and this is our main data, which is then further analyzed by Stokes integrals. So I don't want to talk about what this integral is, just forget it at the moment. And after developing the first geoid, then we need to do some fittings. This is really tricky because we have many islands with very complex topographic seabed, and at some regions it is easy to fit the local geoid into the mean sea level. But in another areas, like in the eastern Indonesia, where the oceanic currents, waves, and the tidal is really complicated, it is difficult. So in the intermediate step, we reduce the land geoid, every island, into local mean sea level. And then we homogenize all these local geoids by using some tide gauge stations. At the moment, we use almost 100 tide gauge stations to reduce or to fit our local geoid into mean sea level. And of course, this will be really problem, but this is the best we can do. First, we reduce it into the local fitting, and then we try to generalize so that we can have seamless geoid around Indonesia. And in order to validate our geoid models, we compare it with the GNSS leveling. So because I think most of you have understood that combining GNSS and leveling can also produce geoid. So this is two different techniques. Thank again to BIG that they have been conducting some leveling campaign, GPS campaign around some islands. And for developing this in a Geoid 2020, there are some leveling survey that have conducted by BIG. Of course, there are different types of leveling surveys, but anyway, all these surveys can be used to validate our geoid models. So we have one in Sumatra, Java, and Bali, and 2 loops in Kalimantan, and also in Sulawesi. So this is, I think, the external validation, which is at this time the best we can do to validate our geoid model, so that we can check how accurate our model is. So this is just the final result of the INA Geoid 2020. We compare in some islands the geoid, and of course the limitation is our validation is only along the leveling line. So if we say that the accuracy in Sumatra is, say, 20 centimeters, this is not the whole Sumatra, but just only leveling line, just only a few percent of the Sumatra area. So, but this is something like a sample that we can we can take, because we have really no choice to follow it for the whole island. But at least from this sample of the islands, we could see that the accuracy of the INA-GEOID 2020 is around 30 centimeters. But anyway, this is the best that we can do, especially people from BIG. They have been doing a great job to improve our geoid models. You can imagine starting from 4 meters and then a little bit better into 1 meters, and now it is around 30 centimeters. I think it is good. But of course, our current geoid model, there are many things that have to be improved, and we try to develop or to improve our current geoid models. There are some considerations, like we try to introduce more gravity observations. I think our colleagues from BIG will always conduct airborne gravity survey, terrestrial survey, and this is good because then we have much more database come into our server. And on the other side, we also try to consider the oceanic, the ocean geoid. For this case, we use satellite altimetry, and also we can use shipborne gravity, which can be free download from the USA server in USA. So we tried the best we can do, because we need also accurate ocean geoid, because our oceanic characteristic is really very complex. So that is one of the reasons why we also need to consider the ocean geoid. And then we try to make it seamless with the land geoid. And of course, this is a very, very tough task. Not easy, but at least we can try step by step. There is some consideration that we try to realize in our next INA-GEOID 2025 or 2026. So far, we cannot tell exactly which number in the last digit, 5 or 6 or 7 or 10, but at least we try to make it perfect. And accuracy goals for the next INA-GEOID 22X, hopefully it can be better than 10 centimeters, hopefully. And for these plans, we have been conducting some preliminary works. Let me explain one by one. So this is our plans to improve our current INA-GEOID model. As I said, we try to combine the land gravity survey, which had been done by BIG, and we try also to include, to analyze the data from satellite altimetry. So in this case, we have tried to do some exercise and some calculation just to see if it is possible to use altimetry for improving our INA-GEOID. In the case for satellite altimetry, we used repeat mission of the satellite altimetry like Cryosat, SARAL, and so on. And the most important data set is, of course, from Geodetic missions. At this time, we try to elaborate or process the data from JSON 1 and JSON 2, because those satellites will provide a very dense altimetric points from which we can develop our ocean geoid model. And this is our first result working on ocean geoid. We tried first to calculate what we call the vertical of deflections, which is just the gradient of the gravity along north-south and east-west, west-east. You can see it's very complex topographic from this result. This will be further processed, analyzed, along with the data from land gravity observation. And hopefully we can have seamless Indonesian geoid covering land and sea. And also we try to do some simulation, the effect of the expanding our gravity data in Java, we have a good sample because we have many gravity observation, line observation in Java Islands, airborne, or terrestrial gravity, absolute gravity, and this is very nice data set where we can use it for try to see if how accurate, how improved if we use many data. At the moment, we have a terrestrial observation every 5 and for airborne every 16 kilometer line spacing. This is very good. And this is our first validation or investigation, the different data set. The first figures is if we use all the data set that we have, and the second one is we only use the terrestrial gravity data. So this comparison show that if we use all the gravity that we have, the gravity data that we have, then we can go to the formal errors approximately 10 centimeters. And of course, this is, I think, to be too good, 10 centimeters. But this is the result that we have at the moment. So this can indicate that collecting new data set, which has been really good, been done by BIG, can help to improve our inner geoid. And we go also to analyze the numerical aspects because mathematical modeling and the way we work with this mathematics will also contribute to the errors. And so far we use the basic approach using Fourier transform, and in the next, in a geoid, we will try another method, like least square collocation, and then we try to use different spherical caps and so on and so on. So this is two techniques, but this is the thing that we need to do in trying to improve our geoid models. And also, BIG has already conducted more leveling campaign, and this will be really helpful. This will be helpful because then we can have some samples data for us to validate. And this is the last problems that comes to our considerations because as I mentioned earlier that we fit the geoid into local islands, and then we need now to consider connecting between sea level observation. So again, this is our ideas, and these ideas has not yet been tried, but we will do it soon. There are many things that come to our minds how to connect between two sea levels, two local sea levels. We can use hydrodynamic modeling, or we can use the mean dynamic topography and so on and so on. I think for this we need to discuss with expert in oceanographer or marine science and so on. I think I think this is my last presentation, and thank you very much for your consideration.
Thank you very much, Pak Dudi. I feel that here on geoid competition between Indonesia and Australia because we Dr. Riddle presented Australian geoid in accuracy with 8 to 13 centimeters, Indonesian geoid right now 30 centimeters, but improve to the next future to 10 centimeters, hopefully. Hopefully also Australian geoid also improve to better precision. And now Japan geoid. Okay. The next presentation is sea level modeling developments presented by Sumiyoshi-san. Please.
Thank you so much for introduction, Chair. And so I'm so happy and honored to invite making a presentation for you. Except especially for me, this is a first community for me. So today I talk about the sea level model development for hydrographic surveys in Japan. So now I'm working in IHO, International Hydrographic Organization, but today's presentation is very technical, and so when I was doing research until this March. So, in my presentation, so I'm happy. So I hope you feel what hydrographic surveyor thinking and what hydrographic surveyor thinking about vertical datum. So let's start. At first, just to be sure, I talk about the vertical datum in hydrography. So at first, the important thing is a nautical chart is a subject map for navigation safety. So that's why the vertical datum in nautical chart is very complicated. For example, the vertical datum of depth is based on the lowest water level because to avoid the ship hitting on the ground. So the vertical datum of depth is LAT or something, and on the other hand, the vertical datum of bridge height is higher water, so HAT or something, because to avoid ship of the mast of the ship hit on the bridge. But the important thing is that in vertical datum in nautical chart is based on local water levels, while the vertical datum in land is gravity-based geoid. This is sometimes misunderstanding between hydrography and the land surveyor. And recently, we mainly two main needs for sea level modeling in hydrography. One is the survey aspect, and the other is the navigation aspect. And in depth, just a moment. Yeah. So the left, I talk about in the depth measurement, we like to use GNSS ellipsoid height and vertical chart data model because for fast and efficient hydrographic survey, including navigation response. And also, this is a little bit different from hydrographic survey, but the marine construction part in Japanese government, the real-time construction in ports and harbor is thinking necessary by using GNSS height from the chart datum. So this is a survey aspect. And the other thing is maybe you someone already know S100 standards data modeling, especially for S104, the water level information prediction for the surface navigation is set. And this is related to the under-keel clearance, the maximized under-keel clearance of the ship. So, but today, so I focused on the survey aspect. The next slide is, so I talk about the ellipsoidally referenced hydrographic survey. And so before that, the classic conventional hydrographics, I talk about the classic conventional hydrographic survey. So the hydrographic survey, so by using sonar, vessel-equipped sonar, we measure the depth from the instantaneous water surface. And then simultaneously, we need to measure the tide using a tide gauge. And also to determine the chart datum, we need a benchmark tied to the chart datum. So we need 3 components for the traditional hydrographic survey. On the other hand, ellipsoidal reference survey, we call ERS. The difference is we don't need a tide gauge because by using the GPS ellipsoidal height, we can measure the water surface. We call sometimes we call GNSS tide. And by using this information and chart data model pre-built, we can measure the depth from the chart datum. This is a basic concept. And this technology being introduced in the leading countries, and not all countries, and now being researched in Japan. And I'd like to explain the difference between ERS survey and conventional survey through this big earthquake event. 2014 New Year occurred Noto Peninsula earthquake. This earthquake is a very, very big earthquake. Moment magnitude is a 7.6 meter. It's a 7.6. And so the very special event is the very huge uplift was occurred. For example, the upper slide, the coastal line going to the seaside, and the uplift is 2 meter. And also this pier uplift is approximately 4 meter. So this is a huge earthquake. And what is the relationship between the hydrographic survey and this earthquake? One of these is so we lose a lot of chart data due to the Noto Peninsula earthquake, and due to the earthquake, the uplift moved more than 50 benchmarks tied to the chart datum, so making benchmark unusable. And ellipsoidal height measurement and tide observation has been necessary to restore the benchmark, and this means the chart datums. But some of benchmarks remains unrestored still. So this means that this is very difficult. It is very difficult to obtain sufficiently precise bathymetry quickly with conventional hydrographic survey method. But So this is the advantage of ERS survey. So when we use ERS survey, we already have a chart data, building high quality chart data model. So the chart data model is not affected by lift too much, so allowing for the rapid bathymetry with high quality. So we think the key is rebuilding the high quality chart data model, assuming the precise GNSS measurement, kinematic GNSS measurement is necessary. So in this slide, the next slide, I talk about focus on the chart data, building the chart data modeling in Japan. This is a basic concept of vertical chart data model. The concept is very easy. This is a mean sea level height. This means a dynamic surface topography. Added geoid model and reduce Z0. Z0 means a tidal range. And we can get the chart data model. But the next slide, I talk about the detail of these components, especially for the mean sea level height. This is a very difficult thing. And when we calculate the mean sea level height at the tide station, we use 5-year mean sea levels from 2060 to 2020 by the permanent tide stations. And also benchmark height from the, this means a zero level at the tide gauge measured by leveling to the vertical reference point. And especially in Japan, some area has a high cluster deformation, like northern east part of Japan. The benchmark heights were collected by the vertical cluster deformation to match the mean sea level epoch at 2016 to 2020. This collection is important. And now, so when we get, now we get we calculate the chart data model for in the 12 port area throughout the Japan left on side. And then, so we did the verification test for the of the chart data model. So to compare the depth by ERS and the depth conventional survey method. And these differences were within the range of S44, IHO S44 special order, the most strict the survey order, survey precision, vertical precision. And the equation is like this, but for example, depth is 20 meter. Then the threshold is around 30 centimeter. And also we check the GNSS tide measured by survey vessel and the tide station level. And then this is the data, and the tide, G's tide level is matched very well. We confirmed. So this means that generally we can calculate it the reasonable chart data models. We have a little bit some issue, but generally we can get the reasonable chart data model now. And the next slide is a future challenging mean sea level height modeling. Maybe in the morning session, Mr. Miyahara-san already talked, but I talk about a little bit detail. So, for example, in the mean sea level height is not so varied in spatially in spatial direction. So now we use uniform modeling. And and then the left bottom part is Tokyo Bay. Tokyo Bay is a little bit the slope of the mean sea level height there. So we use now team modeling. But to calculate around Japan, so as you know, we need to considering the influence of glacial current channels, tracking. So to appropriate modeling of very complex mean sea level heights around Japan. And also, luckily, we will have a high accuracy chart data model with the use of the Geoid 2024. I think this is very useful for our chart data modeling. So this is a summary for my slide. The sea level model for ellipsoidal hydrographic survey is researching and developing in some countries, including Japan. And in Japan, chart data models at each port on a trial base, but being tested for the introduction of ERS, and these are being verified through the comparison between the conventional survey result. And to create a higher quality chart data model, it is necessary to consider regional characteristics such as terrestrial deformation and oceanographic effect, as well as to use high precision geoid model. That's all. So thank you so much for your attention. Thank you.
Thank you very much, Sumiyoshi-san, for the interesting presentation. I think, after explanation of geoid models, now we get the explanation about the sea level model, produce chart model, and also the geoid model of Japan. And I think joining land and sea will be ready in the future. Thank you. And the next speaker, the last speaker for this session, the Indonesian tidal model developments will be presented by Pak Wiwin Windu Pranata. Please.
Okay. Good afternoon, everybody. So I would like to present about the development of Indonesian tide model. So This is actually motivated by, as Padudi said, we want to develop a Geoid model also for ocean Geoid model. So we have to develop one tidal model because it is important for the corrections of the altimetry data. Of course, we have some global tide models, but when we test it in our oceans, in our waters, the existing global tide model have an accuracy more than 15 centimeters, particularly in shallow water and close to the coastal area. And whereas the accuracy of the altimetry satellite itself is about 2.5 to 7.9 centimeters. And then also related to the previous presentations, we want to also develop the Indonesian tidal data model. It is important for our coastline along Indonesian islands. We want to determine the coastline based on the highest water level or the mean sea level or the lowest water level. And also we want to also develop like the one in Japan for this Indonesian hydrographic separation model. So we want to have where the lowest astronomical tide related to the geoid or to the ellipsoid, for example. And that would be important also for the GNSS tides. So how do we improve this tidal model? We use also the model from the satellite altimetry. So we want to have the combination of the satellite altimetry, which satellite altimetry that should be correct, for our waters. So it is tested to minimize the relative error between the satellites. And also we try to use the long track altimetry multi-satellite data. So we use multi-satellite data and we use the data along the track, not only on the crossover. This is we did to improve the resolutions. This is more or less the methodology. After we have the long track multi-satellite altimetry data, we have the sea surface height after we did some correction, of course, for the data. And then we did the tidal analysis for those sea surface height data. We do some screening, crossover adjustment, crossover analysis in order to have the best fit altimetry data to have the best the best tidal components from each satellites, and then we try to compare all those satellite data, all those tidal components from all the satellites using this relative error analysis between satellites in order to select the optimal satellite combinations, because if we use all the satellites, and then the result is not really good because some satellites has much error compared to the others. And then we have several satellites with different temporal resolution, different spatial resolution, and we have different also length of data and so on. So we have to select what kind of combination between satellites that would be optimized for our waters. And then after we have the combinations, we do the tidal modeling combined with the tidal stations data, and then we do the model validations of those tide model. This is all the satellites we use, all the TOPEC JSON series, and then the Sentinels, GFO, and VISAT, and so on. We use also 160 BIG permanent tidal stations. Previously, yesterday, BIG has already 290 tidal station data, but from them, we use all the stations with the period of 5 years of data, at least with 1 hour interval. So it is only about 160 tidal stations. So we do the tidal analysis for the tidal stations and also for the satellite altimetry data. This is the crossover analysis to make the, so I will not explain about that. So we try to also to calculate the relative error between satellites. We have reference satellites to compare, to select the best satellites combinations. So this is more or less the first single satellite crossover adjustment. We want to have which one is the best satellites compared to each other by comparing the ascending and descending tracks. So we have Topex and JSON series, the smallest one, and this is will be used as the reference satellites. And then to determine the multi-satellite combinations, we do this relative errors analysis, and we can see that between those satellites, when we compare to relative to the JSON group, we select this satellite group 3 as the best combinations. So that would be the combination of the satellites. This is how we do the tidal modeling. So after we have the components from the tidal analysis, and then we do the gridding with the spline tensions and to the Gaussian smoothing. So at the end, we have 2-minute resolutions of the tidal data. Whereas for the shallow water tide model, we use we do not use the altimetry data to calculate the shallow water tide model. We use the existing global tide model to calculate the shallow water tide model. For the validation of the tidal model, we compare with the data from the tidal stations to calculate the sinus and cosinus arguments. At the end, we calculate the accuracy of each tidal components and for all tidal components. This is more or less the results for the. So this is the accuracy assessment after we compare with the tidal components from the tidal stations. This is the satellite group 1, 2, and 3. From here we can see that the satellite combination within the group 3, this is the best combination to have the all components in the less or the smallest error compared to the tidal station data. Of course, we have to keep in mind as well that the tidal stations data, of course, also contain errors when we compare to the satellite altimetry. So if we compare to the other global tide model, for example, here for the tidal model FAS 2014, TPX09, EOT, and so on. For the satellite group 3 with the combination with tidal station, we can say that we have better accuracy. For the overall accuracy, it's about 11 centimeters. So after we have the tidal components and also the tidal model, we try to estimate or to calculate the tidal datums. As Pak Arif previously said, in our regulation, at least we have to determine these 5 tidal datums, starting from highest astronomical tide, and then mean high water spring, mean sea level or mean sea surface, mean low water spring, and the LAT. All of the calculations will be based on 20 years prediction from the tidal components that we produce from the tidal model. And this is the result of the HAT, MHWS, LAT, and MLWS S, if it is referred to the mean sea surface, so we have the height of minus 4 meters to 4 meters for the whole Indonesian waters. And then this is if we refer the HAT, HWS, LAT, and MLWS through the ellipsoid. We use WGS 1984 for the ellipsoid. So we can see on the eastern part is much higher compared to the western part. This is referred to ellipsoid. So, and the last one, this is from the Geoid. We use Geoid, so the one that previously presented by Pak Dudi as the reference for the Geoid. And then this is the result, more or less, of our tidal datums. So for the tidal datum, we also try to verify it with the tidal datum resulted from the tidal stations, calculated from the tidal stations. We use these 160 tidal stations to compare. And in total, we have about 12 centimeters in HAT. But since we know there are some tidal stations located somehow not really represents the ocean tides, so we remove what we call the outliers. After we remove some tidal stations that we call outliers, then the accuracy is more or less improved from 12 to 11 centimeters. And then for LAT, we have 15 centimeters improved to 13.9 centimeters. For mean high water spring, it's 9 meters and 8 meters. For mean low water spring, it's 9 meters and 8 centimeters. So why we have to remove some tidal stations? Because some of the tidal stations located in very narrow bay, for example, because our tidal models has a resolution of 2 minutes, whereas this bay is really small, it's less than 2 minutes. So we remove some tidal station that is located on the river or on the small bays or on the small straits and so on. So this is what we try to improve the accuracy of our tidal model or our tidal datum model. So I think that's all from me. Thank you very much.
Thank you very much, Pak Bibin, for your presentation. Now is the time for discussing together. The floor is open. Anyone have? Okay, one. The other? Okay, please.
Alex Lepodat from TU Delft. I have a question for Mr. Dodi Darmawan for the INA Geoid. It's rather a technical question. I was wondering if the leveling lines that you use for the validation, if they come from current leveling campaigns or if they are from older campaigns. And a second question is, you said you use about 100 stations for tying the local mean sea level. And we know there are about 300, so how did you decide on this number of 100 stations? Thanks.
Okay, thank you. Please respond.
Yeah, thank you. Thank you very much for the questions. The first question is the GPS leveling campaign was conducted 2 years ago, so it is quite recent observations. I think our colleagues from BIG can correct me if I'm wrong, but the leveling campaign was conducted 3 years ago, and then we have current GPS leveling in Borneo Islands, which I think the observation was conducted this year. So, and the second one is we select some station like Pawin mentioned. There are some bed tidal station. Bed in terms of location is not perfect for doing tidal station and so on and so on. So in principle, we selected the best tidal station for our geoid fittings. So hope it can help.
And by best, you mean the longest time series, or?
Yeah, the longest time series, at least we need 2 years tidal station observation, and it is located in the open sea, relatively, not in the narrow strait like Pawin mentioned it. Some stations are located in not good in terms of oceanographic condition, so we remove such stations.
Thank you.
Yeah, thank you.
Okay, thank you. Any other question? No? We have still time about... oh yeah, please.
Thank you very much for presentations. I also have a very technical question to geo development. So what is the tidal system of your geoid? So usually geodetic leveling tidal system is mean tide. And GNSS positioning, it's non-tide. And what about the tidal system of your geoid model?
Sorry, can you repeat the question?
So we have to handle a tidal system to construct the geodetic reference frame. And usually the height system constructed from geodetic leveling, tidal system is mean tide. But in case of geoid modeling, usually tidal system is tide free. But if we want to compare and make the two systems more consistent, it is better to translate the tide-free system to mean tide. Because in case of Japan, we first developed a gravity geoid model, tide-free. But the difference between the GNSS leveling geoid height and the gravimetric geoid height has some biases. And after the transformation from tide-free geoid to mean tide geoid, the difference getting much smaller. One of the reasons is we just use a single tidal station as a reference, so the difference getting larger once the distance from the origin is getting far. So do you have similar experience on what do you handle your tidal system in your geoid model?
I thought this question is for Pawin, but actually for me. Sorry. So that is why in my last presentation, we need to make a connection between sea local observation. So this is one way for us to do tide-free station for deploying our geoids. So thank you very much for your suggestion. That we will do it soon. Yeah, thank you.
Yeah, look, in Australia, the gravimetric part is a combination of some of the satellite altimetry for the tidal observations, and I believe that we take a mean tide from those as well, so it's almost tide-free satellite altimetry that goes into the gravimetric component.
Okay, thank you. Any other question? Pak Perry? Quiet. Anyone? No? Okay. I have just a question for Dr. Riddle. Because Indonesian geoid, I think, less accurate than Australian. Therefore, I ask for Dr. Riddle. As a continental country, Australia has diverse terrain and extensive coastal area. What are the main challenges in geoid modeling for such a large and diverse region, and who are these challenges addressed in your research? Please.
Yeah, thank you very much for the question. I think we have one of the longest coastlines in existence in terms of the trying to map the entire continent. I think the challenge comes from the diversity of data that you need to draw on and the combination of that, and then propagating the uncertainty in that combination. So I think there's still absolutely areas for improvement in the uncertainty propagation aspect, but the integration and combination of different data sets. And I think we're excited by the new satellite missions that are coming on board. So I didn't mention it in my presentation, but we're looking forward to the availability of the SWOT mission, so the surface water and ocean topography new satellite altimetry mission, which will help improve the coastal and intertidal regions in terms of the satellite altimetry parts.
So combine also with the satellite altimetry data?
Yes.
Yeah. Okay. Okay, thank you. Any other question? I open from the floor. No? One question for Sumiyoshi-san. I think in geodesy and topographic mapping, the vertical datum is modeled using both the geoid and ellipsoidal height. Yeah. With the availability of a local and global geoid model, it is possible to transform between ellipsoidal heights and altimeter height, although accuracy may still be limited in certain area. However, in the nautical chart, the chart datum is typically modeled locally, and chart datum is locally. I never hear about the global chart datum. Global geoid is yes, but the global chart datum is not established yet. How can we transfer depth based on ellipsoidal height in depth based on chart datum when no global chart datum model is available? For example, in the remote area where the local chart datum is not available.
Thank you for the question, and this is difficult to answer. But today I introduce the chart data model. Yeah. Chart data model is from ellipsoidal height. In this case, WGS84. By using it, if we have this model, the chart data model, so for example, around Japan or around Indonesia, so we can convert the chart depth to ellipsoid height. Okay. You understand? So, okay. So this means so after that we can convert any what you want datum. Okay. This is one good use of case to develop one motivation to develop the chart data model. I think. Yeah.
Okay. Thank you very much. Our time is up, and applause for the presenters, for the speakers. And of course, thank you for all of you for your attention. Thank you.
Thank you. Please give a round of applause to all of us. A big thank you to Mr. Hafid for steering this session so effectively and keeping us engaged. We are grateful for your invaluable contributions. Now, to all speakers and moderators, please come forward to the stage, and I would like to invite Mr. Anton Wijanarto, the President of UN-GGIM AP, to deliver the token of appreciations to all speakers and moderators. And now please have a group photo session together. Please give your smile to the camera in 1, 2, and 3. Once again, in 1, 2, and 3. Thank you. Please give a big round of applause to all of us once again. Okay, distinguished guests, ladies and gentlemen, let's recharge ourselves with an afternoon break. And please return at 4 p.m. to continue to the 8th and last station for today. Thank you and enjoy the refreshment. right, ladies and gentlemen, the next session is about to begin shortly. I request to all of you to be back to the room. Ladies and gentlemen, for those of you who are still outside the room, I kindly request you to be back to your room as we will begin the event shortly. Ladies and gentlemen, the next session is about to begin. We kindly request all of you to be back to the room and have a seat. Thank you. Distinguished guests, it's already 4 p.m. right now. We kindly request all of you to be back to the room as we will begin the last session. Ladies and gentlemen, there is a little information for you. We have the Wall of Fame outside this room, and you are encouraged to write some suggestion or your experience here and what you feel about this event in the, and write it on the Wall of Fame. Distinguished guests, ladies and gentlemen, now we have come to our last session, the 8th session, Advancing Geodesy for Coastal Protection. This session will be moderated by Mr. Evert Mulder, the Geomatics Manager of Geodesy and National Mapping, Singapore Land Authority. Mr. Evert Mulder, I'm sorry for the bad pronunciation, is a geomatics specialist based in Singapore, excels in data acquisition, analysis, and management to support infrastructure and environmental projects. He has contributed to the National 3D Mapping Project and organized key events like the 2019 3D Geo Info Conference and the 2020 Multi-GNSS Asia Symposium. So without further ado, let's welcome our moderator, Mr. Mulder. The floor is yours.
Thank you so much. Good afternoon, distinguished guests, ladies and gentlemen. Welcome to this 8th session on advancing geodesy for coastal protection. I'm Evert Mulder. I'm a geomatics manager at Singapore Land Authority, as the introduction now shared. In my work nowadays, I focus mainly on geodesy and GNSS and advancing related capabilities and efforts across the whole of government in Singapore. And it's my absolute pleasure to be here and to be moderating this event. Before I start, I would first like to say a big thank you to UN-GGCE and the BIG team for giving us this opportunity to have this session. I think the organization has been very good so far. I think you've set a very good standard for future events, very high bar. I would now like to invite the speakers for this session, Mr. Alex Lapadat, Dr. Feng Luija, and Dr. Oi Sing Kiat to join me here on the stage, please. Thank you. Okay, I didn't prepare any slides, as I do not want to steal any of my presenters' thunder, so to say, but please allow me to set the stage a little bit and then explain a little bit on how the content of this session came together. The overall theme of this workshop, as we all know and heard many, many times, is joining land and sea, and it is obviously very relevant, but also especially in Singapore. As a small island state, we are in a situation where 30% of our land is within 5 meters of mean sea level. And so we are critically vulnerable to sea level rise. And the research has actually shown that by 2100, the sea is expected to rise by 1.15 meters, and that's excluding extreme events. If you include those, the number actually changes to 4 to 5 meters. So that means that if nothing is done, by 2100, we may be in a situation where we would lose around 30% of our land. And that's obviously not something that we want. So yesterday I already briefly shared on some of the things that we are doing in-house. But besides that, we are also working with various experts, both local and overseas, to work on various projects in this scene. And it's my privilege to have 3 of them here today. And they will be sharing on findings and capabilities and provide valuable insights on how to potentially address some of these challenges that we have spoken about earlier and today and yesterday. Originally, the plan for this session was that it was going to be a bit different and having separate sessions, each of them having questions afterwards, but I just heard that we have a bit more time, so we'll do it as per normal and have a discussion at the end. So we'll first have 3 presentations, and afterwards we'll have a discussion session. So please keep your questions to the end. Without further ado, let's get started. So our first speaker will be Mr. Alex Lapadat, who is a PhD candidate at the Mathematical Geodesy and Positioning Group at the Technical University of Delft in the Netherlands. And as a part of a collaborative project called the Three Sisters, which brings together geodetic expertise from universities and organizations in the Netherlands, Singapore, and Indonesia, he will present on geodetic infrastructure and procedures for vertical land motion and sea level rise monitoring, current capabilities, and future solutions. Please join me in welcoming him to the stage. Alex, please.
Good afternoon, everyone. Thank you, Evert, for the introduction. I hope there is still a bit of energy for the last session. Today, I will strictly speak about current infrastructure, procedures, and various products that we all use for estimating vertical land motion and sea level rise for low-lying countries. And we have heard already throughout these 2 days that basically sea level rise and vertical land motion are entangled processes. Perhaps this is also because the way in which we use the techniques, mainly independently. So this presentation will strictly speak about using independent techniques, and will propose a solution at the end of it on how to develop products that can help us look at vertical land motion and sea level change. So, with further ado, let's start by examining the capabilities of the techniques and the infrastructure in low-lying countries, mainly Netherlands, Singapore, and Indonesia. And I will start by, with a summary table of the most common techniques we use in these 3 countries to estimate elevations and their spatial temporal derivatives. Techniques like spirit leveling, tide gauges, gravity, but also more modern techniques such as GNSS, INSAR, and extensometry. It's very important to distinguish that all these techniques, if we look at their infrastructure, they do not really measure directly the land surface, but specific objects. For instance, for spirit leveling, what we do, we estimate the height difference between 2 benchmarks, so mainly 2 bolts that can be placed anywhere. And for GNSS, for example, we determine a 3D position of an antenna and not necessarily the land. So, if we want to look now on how all these techniques have evolved in the 3 countries, I prepared basically this figure. It shows how each technique has evolved over 3 centuries or 2.5 centuries. And what we first get from it is that in the first half of the figure, techniques like tide gauges and leveling were prevalent. And that was mainly because at that time, 19th century and 20th century, these 3 countries, and not only, were looking at static applications, trying to solve applications like mapping, construction works. So not really what we are dealing with right now. In the second half of the figure, we see this sharp transition between GNSS, from the classic techniques to GNSS, INSAR, and extensometry. And that was mainly our shift of focus from static applications to dynamic applications, such as tectonics or earthquakes to mitigate disasters for our communities. So far so good. I think at this point we know a bit about the techniques that are used. We know also their temporal coverage. So it would be good to make some remarkable, to point to some remarkable results in the 3 countries with respect to infrastructure and the product. So in the Netherlands, we put a lot of effort in designing various radar infrastructure, coming in the form of radar transponders and integrated corner reflectors, which I'll talk more about in the coming slides. And this kind of infrastructure was supporting our national subsidence maps. In case of Singapore, the smart country policy was basically pushing Singapore towards developing a national DEM. They have 2 versions of it, and a 3rd one is undergoing. And in case of Indonesia, very close from here in Jakarta, there is an extensive extensometer network, which is measuring the land subsidence down to 350 meters. So that is outstanding in our eyes. In the Netherlands, we're a bit jealous in this, to be honest. And on top of that, we also know already that the country has given up on leveling, and they are developing a national Geoid model. So these are already outstanding products that the countries were able to basically
put together. And at this point, I guess you question, okay, it sounds like we have all the infrastructure, we have the results, we can start looking at vertical land motion, but maybe it's not the case. So there is a problem, mainly that most of these techniques work independently, linked to different datums, and that's what I'm trying to explore with you in the next slides. So historically, each country was developing their vertical reference datum by doing water level measurements, and they were fixing this elevation plane at a specific epoch. From this, they materialized it, they created it by placing reference benchmarks on the Earth's surface, and with that they started doing leveling to different objects to get elevations across the land, let's say to tide gauges. Now, the problem with this kind of reference datum is that maybe our reference benchmarks are actually moving over time. So any elevation change happening at the reference benchmarks, if we don't take them into account and we use this data for dynamic purposes, we'll end up with biases. Okay, so let's look into future. We're going to use INSAR. We're going to look at the elevation changes across the shore. But we don't have to forget that basically all the INSAR products are linked to the radar datum. And in this case, the reference is basically a reference pixel in an image, which can be floating. So that's another problem, another datum, another data type. Thirdly, we have heard a lot yesterday about placing GNSS sensors at tide gauges, that they can help us with getting vertical land motion solved and clean our sea level measurements. But again, we have to not forget that these measurements are referenced to yet another datum, the ellipsoid, which is a geometric datum. So we are faced in this, this is the situation. We have a lot of techniques, we take them all, and we want to do something good for our communities, but they all work independently. So how do we connect them? How do we connect them? That's the question. Let's go into some solutions. Before doing that, the summary is the following. We have lots of historic data, and our philosophy in Delft is to not throw anything away. Second, at this moment, we have INSAR, we have LiDAR that can actually measure the surface of the land continuously, but there is no connection between this historic data and the continuous monitoring. So the solution that we propose comes in the form of an infrastructure solution. It's called the Integrated Geodetic Reference Station. And it's basically a benchmark which is able to and allows us to connect various geodetic techniques in one point in space that can be continuously monitored. Let me explain how this benchmark actually works. So the deep foundation of this benchmark can be leveled in order to reference it to the vertical datum of the specific country. And the same applies also for gravimetric measurements. We have a benchmark at the plate of this benchmark. Good. Then the horizontal surface of this benchmark can work as a ground control point for LiDAR. And by that, we would be able to connect all the LiDAR point clouds to the same vertical datum. Then thirdly, we would be able to use the corner reflectors to back amplify the signals of the radar signal. And by that, we would be able to use a physical benchmark in the radar image instead of a floating pixel. And lastly, we could also use the GNSS sensor on top of this benchmark to connect all these techniques in an ellipsoidal datum based on the application, and also monitor any kind of inherent movement of the benchmark over time and correct for that. So it seems that this is a potential solution to be able to integrate all these techniques that I presented in the beginning into one specific point in space. And yeah, I hope this is basically a future inspiration for other designs that can solve other problems, maybe like an integrated tide gauge station. So this is a sketch of such a tide gauge station, same concept. So bringing the IGRS in the middle of this tide gauge, having all these techniques measure the same benchmark, which is mainly shown here in yellow. This is basically the structure foundation. By that, we'll be easily be able to separate vertical land motion from sea level change at a specific point and not have to level every year or do a lot of campaigns in order to solve this issue. But this is, again, a proof of concept, an idea, and I hope this is an inspiration for what we have done so far with the IGRS. So it's basically fictive. So yeah, I hope that I showed how integrated infrastructure could be a solution to bridge the gap between past and present solutions that we have nowadays. Yeah, and this brings me to the conclusions of this presentation, which are, we have shown that countries like the Netherlands, Singapore, and Indonesia are able to develop great products, but most of the techniques that we use work in independent datums. And the solution that we've shown is that having integrated benchmarks like the IGRS would be able to bridge this gap. And I hope I convinced you this is maybe a way ahead to design such infrastructure, deploy it, and very important, maintain it over very long time spans. And by that, we'll be able to bridge from fragmented solutions to unified solutions and let basically Geodesy serve our communities. Thank you very much.
Thank you very much, Alex, for that insightful sharing. Please take a seat. Next up, we have Dr. Feng Luija, Assistant Professor at the Asian School of Environment and Principal Investigator at the Nanyang Technological University's Earth Observatory of Singapore. And she will be talking about one technique specifically, namely GNSS, and how you can join land and sea using that. Luija, please.
Thank you so much, Albert. And good afternoon, everyone. It's my great pleasure to be here. And thank UN-GGCE and BIG for organizing this event and providing me this opportunity to speak. So my original title was Joining Land and Sea using the Global Navigation Satellite System, GNSS. But after listening to so many talks yesterday and today, I realized my title was meaningless because all the talks about joining land and sea and almost all the talks mentioned GNSS. It's just to what degree. So to be more precise, actually, a better title for my talk should be joining land and sea using a single GNSS station. So what do I mean by using a single GNSS station? Actually, my talk actually followed very nicely after Alex's talk. So what do I mean by a single GNSS station? So first, I want to set up the background by talking about one of the challenges mentioned yesterday. So tide gauge records as one of the longest, the earliest records for sea level has one weakness. Tide gauge only measures relative sea level. So if land is not moving, we know how sea level changes. However, we know land moves too due to tectonics and the GIA change of this. So we cannot assume the land is stable. So this causes a problem. So many people have already addressed we need a tide gauges with GNSS station, like a co-location of tide gauges and GNSS. This is a photo I stole from Australia Geoscience, thanks to Australian Geoscience. It's a station in Tasmania. So it's a co-located station, tide gauge with GNSS. And stations like this are not that many actually globally. So a lot of tide gauge stations, they do not have GNSS stations co-located with them. The other solution is we can find GNSS stations like within very short distance, like a few kilometers away from the tide gauges. So this is a second solution. However, even stations like this are not that many. A lot of tide gauge stations, they do not have GNSS close enough. So the one possible solution I want to propose here is to combine the tide gauge and then GNSS. Just use GNSS alone. So we can use GNSS stations as absolute tide gauges Here are two example GIS stations US established in Taiwan and in Singapore. Oh, sorry, switched. So yes, this is Marina Bay Sands. This obviously Singapore and that one's Taiwan on a cliff. So we can use GNSS to measure the difference between the antenna and the sea level. How does that work? So this is a relatively new technique developed only in the recent decade. I have two versions to explain how it works. This is a simple version. So GSS-IR, GNSS interferometric reflectometry. GSS-IR uses reflected signals to measure sea level. So we are familiar with positioning. So positioning uses direct signals, and we don't want to station the GIS stations close to buildings, close to trees, because we want an open sky. However, for GSIR, GSI want to be close to the sea surface, because when you place GIS station closer to the sea surface, you can get reflected signals from the sea surface. In this way, we can measure how sea surface changes. Okay, so this is a simple version. If you want to hear more about the technical details, I have a detailed version. So how it works. GSIR do not use the traditional phase signals for GIS positioning. Instead, GSIR using signal to noise ratio, the strength of signals. So when the satellite goes from low elevation to high elevation, you see this shape, right? At the low elevation, if the satellite is at low elevation, the signal to noise ratio is low. And when it reaches above your head, the signal is stronger. So you see this, the bell curve shape, which is caused by the satellite elevation changes. However, that's not a signal we need. Okay, so we superimpose. What's superimposed on this bell curve shape is some oscillations like this, like the panel B shows. These oscillations are caused by interference between the direct signals and the reflected signals. And using the signal, the oscillations in panel B, we can actually get what we call reflect height. It is a height between the sea level, the reflected surface, to your antenna. So this is a more technical explanation of how GNSS-IR works. Put this in the reference framework context, what this workshop is about. Using single GIS stations, we can measure both length height changes using the traditional GNSS positioning technique. So we can get R here, a GIS antenna reference to an ellipsoid. And using GNSS-IR, we can get H, the big H here, is the difference between the antenna and the sea surface. Okay, so combining these two, what we can get is the SSH, which is the sea surface height, R minus H. The sea surface height is the height, the sea surface height, relative to reference ellipsoid. So this is sea level in absolute sense. It's not relative anymore. It's absolute sea level. In this way, basically, we can use GNSS as a tag gauge. And we don't need co-locate tag gauge and GNSS anymore. We can just use only GIS stations, can do both jobs. And another advantage is GNSS can get the reference to the reference ellipsoid, not like tag gauge. It has to be referenced to a local datum. So once it's referenced to ellipsoid, we can unify different local datums as a global datum. And we can use this to do any geoid subtraction and to get other types of data. So this, satellite altimetry. So here, the SSH can be determined also by satellite altimetry, which was mentioned a few times in previous talks. I just want to give a quick detour to quickly explain the satellite altimetry technique. So satellite altimetry is a sensor looking down straight and send radar pulses towards the sea surface. So satellite altimetry can measure the SSH very well in open ocean. However, when satellite altimetry signals close to the coast could be contaminated by the land. So the accuracy of satellite altimetry is not that good near the coast. So this is the bridge GNSS can build between the land measurements and the open ocean satellite altimetry, the sea surface height changes. Here I'm talking about kind of the main sea surface changes. However, GNSS can also measure extreme events. This is an example done by my previous colleague, Dong Jupeng. So she used GNSS stations in Hong Kong during a typhoon Mako, which occurred in 2018. So you can see the green dots represent measurements from GNSS, and the gray lines, they are astronomical tides. So the red line is a nearby tide gauge records. So the GNSS records match the tide gauge records pretty well and capture the peak of the storm surge. So this is one example of how GNSS can not only just measuring mean sea level changes, can also measure extreme events like peak sea level changes. Another case is in Singapore. It's again my colleague's work. So she used SIREN, Singapore Satellite Positioning Reference Network, by the Singapore Land Authority. Two stations from SIREN network are placed in a location close enough to the sea level. So she was able to extract the tidal changes from the two stations, and she compared with a tide gauge, the Tanjong Pagar tide gauge, the green one, and with the two GNSS records. We can see, even though Singapore is really small, but the changes, the sea level changes along the Singapore street actually is big, not small. It's not negligible. You can see the amplitude, the annual amplitude change from red, which is the station SNSC is the one in the east, and the amplitude increased towards west. Lastly, I just want to say the take-home message for my talk is, I think GNSS, which was not mentioned at all in previous talks, could be very useful in terms of joining land and sea, working together with other data sets which have been mentioned many times towards the goal of unified global height data. My last slide, I forgot about this. So this I want to say is, in fact, actually Indonesia, you already have a lot of GNSS stations because you install the GNSS station on top of tide gauge, right? They are GNSS stations, can be used for this purpose. And if you want to install more GNSS stations, don't install on top of tide gauge, because then you duplicate records. And install in data gaps where you don't have tide gauges. Yeah. I also want to show there are already a lot of results from Indonesian scientists using GNSS and the BIG stations for looking at sea levels too. Okay, my last slide is about capacity building. So capacity building is a word has been mentioned so many times. I just want to highlight a workshop I organized at the EOS, which we invited about 30 participants from 10 countries, including Indonesia. in Singapore, Malaysia, Philippines, to come to Singapore to have a training on GNSS IR conducted by Dr. Christine Larsen, which is in the middle. She invented this method. Yeah, that's the end of my talk, and thank you so much.
Thank you, Luija. That was great. So we spoke about physical co-location of multiple techniques. We spoke about one technique to do multiple things. And for the next talk, we're going to talk a bit more about data and modeling of data. And for that, we have Dr. Oi Seng-Kiat, Senior Research Fellow at the Tropical Marine Science Institute of the National University of Singapore. And his talk is called Gathering and Using Data in Singapore for Intertidal Flood Models, Datums, Models, and Resolution. Please join me in welcoming him.
Good afternoon, selamat siang, selamat petang. Thank you UN-GGCE and Big for this invitation to talk. I changed the word intertidal to coastal because in the department where I work, it is interchangeable. So I hold a joint appointment actually with the Civil Engineering Department as well as the Tropical Marine Science. So in the engineering department, the institute is called the Coastal Flood Institute. So I will use this interchangeably. This slide was actually put in just to remind us the need and the challenges. We all know we are looking at rising sea levels, potential of land subsidence depending on where you are, increasing risk of pluvial as compared to fluvial flooding. And I will tackle this at the end of the talk when I talk about models. We're looking at intense storms, waves, and if you're in a heavily trafficked, marine traffic area like Singapore, you're looking at ship wakes, right? And I will show you a couple of simulations of that. In this environment, your nearshore bathy topo becomes important. How important and what resolution is something I think I've been asked since I started the project that actually led up to the results that you will see here. We know we need it for engineering design. We will use it for coastal protection. We use it for coastal structures. We will also use it as part of what we now call building with nature structures, right? Because we are not allowed to just build hard structures anymore. We have to have soft defense along with our hard structures. So we will need this when we want to look at flooding, especially flooding arising from water coming from the sea, but also flooding arising from water going out if we cannot handle the water going out from the land. In gathering this data, there are challenges. Some of these are local. Some of these is global. Our equipment resolution is different, right? We've already seen the IOHO numbers at about 20 meters, it's about 20 centimeters. On land, we're looking at millimetric to centimetric accuracy. We have in Singapore, all those blue lines you see there, those are the no-fly zones where you cannot put a drone. You are not allowed to fly a drone. Okay, so we have also no-sail zones. We have areas where we're not allowed to traffic without permission. We have been talking about datums. We will talk a little bit more about datums as we go through this talk. And the final challenge is actually, are the models that people talk about able to utilize the data that you collect and we collect? Okay. So in Singapore right now, this is the present state of data gathering in the conventional survey sense. I think I will skip over most of this slide, but most of you will know this. Typically in the intertidal coastal areas, we will get a surveyor land surveyor to go out at the lowest tide possible, take a data for you and come back up. If not, you hope that your shoreline topography or bathymetry is such that your vessel can come in close enough, your multi-beam can pick it up, and hopefully your LiDAR is strong enough to pick up the signal. Okay? Your problem is if you have to really get everything, because both of these methods tend to result in a small gap. if you want to get everything, the closest thing you need is someone to go out there at the exact same time, and that is almost impossible. Most of us know we deal with a spring nip cycle of about 2 weeks. Within that fortnight, we could potentially have enough movement of the bed that the whole bed moves, right? So we have those issues to look at. So if we have our data gathering windows open and over a large period for a particular site, we can potentially result in large differences in the data collected. So this project started out at the request originally of the Building Control Authority. It was then handed over to the Public Utilities Board in Singapore, because the Public Utilities Board is now in charge of coastal protection. And on board that project, for it to be awarded, MPA and SLA sat on the panel of advisors. So we actually decided to go for a multimodal instrumentation approach. So we started off with the conventional approach, which is to carry out a standard topography survey, but also with LiDAR, on a land-based LiDAR walkthrough, right, to make sure that we can see the same thing, or whether we actually see the same thing. Then from the seaside, we will carry out a vessel. In our case, we replaced the vessel with a USV, the blue picture on the top left, with multi-beam sonar. We bought a multi-sensor shallow draft USV. This USV is 80 kilos, 110 kilos, fully loaded, so 3 people can actually carry out, and 3 people have carried it out into the sea. It actually does very well. We've loaded it with the LiDAR as well as a single beam echo sounder. We have tested it with the multi-beam, and I'm happier with the multi-beam results than the single beam, partly because single beam, as you know, is a single track. And and satellite remote sensing. Remote sensing on the satellite images are the 2 in the middle. Those are of the 2 locations separated over 6 years worth of data. This site had only 2 clear pictures delivered by WorldView. 2. These have been processed by WorldView to the same extent to give you bathymetry in shallow water. As you can see, the color gradient is completely different. This comes from the timing of the satellite, comes from the reflection of the sun on the surface, depending on the timing of the satellite, and basically, without further post-processing, you would not know which one you want to use. The 2 drones that we tried were both multispectral drones. The one in the top is the DJI P4 multispectral, which is no longer available for sale, partly because I think DJI realized that you get a lot more data out of this than you should. The second one is a Wingtra. This is also because of Singapore's restrictions. We cannot fly fixed-wing drones. We're only allowed to use copter drones. So this one takes off as a helicopter and flies as a fixed-wing. And we chose 3 sites. Marine clay and mud on the top, sandy in the middle, and coastal structures at the bottom, also the offshore side. The marine clay mud is the most problematic because we don't have 8-meter-long saltwater crocodiles, but they are now, have grown since I started working in Singapore in 2008. From 1.5 meters, they're now 4. So we no longer step down into those waters for our personal safety. So we have some issues with physical data gathering there. So it was a selected site. So when you look at the various methods, you will see that at both sites, and I don't show you any from the mud, marine clay, because the overlap between the different data sets was almost impossible. Right? The drone, we could not get pictures from the drones where we wanted the drone to go out. But here at ECP, which is East Coast Park, and Seringa is the offshore site, you see that the drone basically gives a good overlap with the topo and to the starting point of where you want to see underwater. The reason we get the underwater pictures is because we post-process the multispectral image, and because the RTK GPS on the DJI portable stand is actually very good. The positioning is such that every picture it takes, we take the subsidiary information and we reprocess and we cut out the picture. I'll show you the picture in the next slide. So you will say, what did the drone pick up at that green line that goes up and down? That is actually the coastal breakwater that was not picked up by the topo survey because they cannot go in and the vessel cannot come inside. Or rather, we didn't drive the vessel inside. Okay, so the drone helps us to cover where we cannot see. So for us, so you can see our image, this is the visual image on the top right, is what the drone sees. We don't take a standard drone picture. We take everything that the drone gives and then we process and correct based on how far out we can extract further with the multispectral cameras. This is the visual, and we stitch them together manually. Everything else is done with open source software. So we have not changed anything else. The only thing that we changed is the post-processing and the extraction of extra images. So for us, as one of the outcomes of the project, what we suggest is in the range where we're looking at, which is ±2 above mean sea level, between ±2 mean sea level, we would take topo survey data as ground truth, have the drone provide us the water depth results from the multispectral camera, and using the drone's own DSM results from the visual cameras to use the above water, merge the three sets together, and you get the picture in the red box, right? So you're basically looking at ±2 mean sea level. So actually you can go deeper if you want to go at extreme low tide, because then you get plus minus, or you get +4 and -2 to roughly your lowest astronomical tide, depending on your tide timing. Right, so this, we think, will be useful for, in Singapore, for maintenance purposes, once we have datum, because all remote sensing items need some sort of ground truth. Okay? So I told Everett I wouldn't spend too much time on this, because one of the things that we're supposed to do in the project was also look for a way to have this adjustable function between datums, right? Because the marine side uses chart datum, the land side has its cadastral datums for their own use, right? So we tested out a couple of things. You can see sort of what you see there. Those are all different values of chart datums as published in the Admiralty chart. It's a bit small, not deliberately so, but because I only have so much space. But I blow up two areas for you, and it's the same problem that we had in the earlier talks, where the closer you come in, the tide gets constricted, the tidal range changes and shifts, right? So we shift 20 centimeters, between 15 to 20 centimeters, along the straits. All of them are closer to 1.51, the difference between chart datum to the land datum. But inside, it's between 1.7 to 1.8 along the Johor Straits, right? So we have this difference in values. Closer into Tanjung Pagar, the value is about 1.6 something, right? So you have the effect of landmass coming into play, right? So these are the issues that we talked about. I think we also brought up the issue in satellite altimetry. This is what we're going to see, right? So if you want to try and do a simple thing, you could do a linear interpolation and create a grid, right? And basically interpolate the points in between. That's one simple method if you're looking at one contiguous line. You can also do a domain focused where you extend the S-Geoid, which has been discussed, right? So these are some methods that we have not settled yet, but we are still discussing what will make sense for Singapore. Okay, so do you use this data for your models? This is Sentosa if you don't recognize it. You will see that the bottom vessel is actually a 150-meter long container vessel traveling at its standard speed of about 15 knots, a bit high. This is traveling at 15 knots, and I know MPA will tell me that it's illegal to travel at 15 knots as it's exiting. Yes, it is. But I also have been on that boat with marinetraffic.com recording the AIS going at 15 to 20 knots. So they do. You will see the high peak frequency waves go in, and all this is just based on chart data. This is not based on high resolution data yet. You will see the Waves go in, and technically, this is where you start to see your shoreline erosion. So your data can be used by high-resolution models. What about when it comes to rain? For rain, because for urban areas, the bulk of the flooding that you see is what you will call pluvial flooding. Singapore prefers to use the term flash floods now, because the traditional flooding term in the hydrological means is a different meaning. Most traditional hydrological models are based on a fluvial flooding concept. Water goes into the drain or the river, and then it comes back out to become a flood. Right? So that's what we normally do. But when it comes to flash floods or pluvial floods, rain builds up as a water level on the surface before it can get into that drain. This is what cities suffer from, which means that actually trying to deal with this is not going to work with most of your traditional models. And the reason I was
Dr. Oy, can you try and wrap it up?
Yep.
Thank you.
I only have one more slide. So the reason it just works for us is because this is where we're going. I'm late for this conference because I was examining students on this concept on the morning of Monday. So if you change this, you change the concept, you actually get to where you could if you are able to provide the DMs, okay? And the final outcome, a potential one, is to be able to use such data, you should want to collect, integrate the data efficiently, have efficient datum, and basically in our world, the hydraulic world, we would like to have a hydraulically appropriate surface, right? So if you're asking me what data I want at what resolution, I would prefer you give me all the data at the resolution you have and let us generate the hydraulic surface we need. Okay? Thank you.
Thank you so much, Dr. Oy. Please take a seat. Are there any questions? We have about 10 minutes. Any questions from the room? There's one over there.
This is a question for Lucia. The GNSS IR is potentially a very, very good technique for getting tidal variation in remote areas. So is there any particular sort of design of antenna that's preferable for that technique? And also, what sort of software is required to process that data?
So, can you hear me? So the beauty of this method is you can use a regular geodetic antenna, or even low-cost antenna could work. Yeah, you don't need a special designed antenna. The other question about software, so Christine Larsen actually released her Python version of software, so everybody can use her code to get the reflect high. Yeah, so it will be because her code, it will be a kind of easy way to implement the methods in many locations, many countries. Yeah.
If I can add on to that, just one little note. A low-cost antenna might actually be a better solution. It seems that the newer antennas, we have just done a tech refresh, and there's questions as to whether it can actually do this, because to some extent it may filter out some of these things that we actually would want in this context. Yeah. Any other questions? Yes, over there.
Maybe like a follow-up on the GNSS. Could you comment on the sea state? Are there situations in which the waves are too rough and where it may not work that well, or is it always very robust?
Roughness of the sea surface. I think there's some more recent studies looking at actually the roughness of the sea surface. It can be used to actually look at the wind changes on the sea surface, but more advanced techniques should be used for just doing the reflect height. Yes.
Yeah.
There are some more recent studies on that. Yes.
Yeah. Well, my question was not so much about using it to measure wind, or but in how far it would affect the quality of the sea surface elevation measurement.
Sea surface is, if you are talking about mean surface or the changes the sea surface height. If sea surface height, it's very good comparable to satellite altimetry. Yes.
So you're saying,
if just sea surface height, yes.
So you're saying that even if in rough seas, your estimation of sea level elevation is still good enough?
Yes. And depends on the temporal resolution too. So if you use a lot of satellites, you can get finer temporal resolution, yes.
Because I would think that even if you use a lot of satellites, but if you have very rough seas, all of those satellites would have the same problem. But I take your word for it.
Storm surge case, it's very quick rise of the sea surface, right? Yes, the example case showed can capture the storm surge, yes.
Thank you.
But it's an average value. Another thing, it's a difference between tide gauge and GSIR. Tide gauge measure 1 point, but GSIR is you scan the surface. So you might not get 1 point, you get an average value of that sea surface changes, yes.
Thank you for that. Over there.
I think just for the information to the forum, we are working closely with the International Association of Geodesy and IUGG as well to host a workshop in Fiji next year in November on G2s, which is tsunami early warning system using GNSS technology. So you're all invited to come there, but no funding, sorry.
It sounds like a good trip. Any other question? Thank you for that. Any other questions? Over there, please.
Yeah, thanks to all the speakers. So great presentations. I just wanted to ask Alex a question. I know you didn't have a lot of time in your presentation. I was hoping you could take a moment to let us know how you're considering the historical data that you mentioned. You don't like to throw away any data. How would you look to then integrate that with this other integrated system that you were talking about? Thanks.
Excellent question. I can give an example by how we deal with our leveling data in the Netherlands. So we were using absolute gravity time series to correct for the changes that we encountered at our reference benchmarks. And with that, we end up with very long time series of elevations coming from leveling. So that's one way to not throw away the leveling campaigns and correct them and be able to provide them to users that need them for dynamic applications. So that's one way.
Thank you. Any other questions? Yes, over there we have one. Can we get a mic to Jotten, please? Thank you.
Hi. Hi, sorry. Oh, yes. Yeah, so I think the SK's presentation did, thanks for my presentations. I think SK's one also mentioned something on the importance of considering floods, right, in the inland. I think that's a sort of a consideration to take into account when we're looking at the integration of terrestrial and maritime domains, right? Because I think, although here we are discussing mostly land and sea, but I think more of the use cases that could come about from the integration of terrestrial and maritime domains also concerns inland waterways and also sort of flooding within in inland areas. I hope that is clear from my perspective. Yeah, thanks.
Thank you for that, Edon. Any other questions? Over there, there's a question.
Okay, thank you. Perhaps just a comment, because what are the needs in terms of geodesy infrastructure for coastal planner and so on? Coastal planner, in the context of sea level rise, they need time. They need to know at what time do I have to protect my nuclear plant? At what time do I have to move this small village or this huge city, and so on. And for that, we have to constrain the still very uncertain climate projection for sea level rise. And for that, if you look at the World Meteorological Organization requirement for sea level essential climate variable, you can see that these are not achieved in terms of accuracy for sea level trends and so on. And if you look at the United States National Academy of Science report about the evolving the geodetic infrastructure to meet new scientific needs, it is explicitly written that sea level rise is the most stringent application for geodesy. And with some colleagues, we have written a paper published in Nature Climate Change where we decomposed the error budget of space altimetry into its different components. And most of them are linked to geodesy. The geocenter of the ITRF, first. Gravity fields, the glacial isostatic adjustment, and the wet tropospheric component, delay, sorry, which are directly related to the geodetic infrastructure and to geodetic products, have to be improved by at least one order of magnitude to meet the requirement for sea level rise, not only for the beauty of science, but to provide constraint to scientists and to society for the IPCC report, and to give coastal planner time to know at what time they have to adapt their coastal region. And I think we could mention in the conclusion of our workshop that the improvement of the geodetic infrastructure, not only in coastal region, but everywhere, for instance, satellite laser ranging in the Pacific or in the southern hemisphere, are also, for coastal planning, very, very important to constrain the geocenter of the ITRF and all the other geodetic products which are very, very important to constrain the pathway that the Earth's system is taking in response to greenhouse gases emissions.
Very good point. Thank you so much. Any last question? Okay, I think I have a general question to all of you, just to end it off. Just maybe from your perspective, give us 3 lines on any kind of other infrastructure or products that you foresee might play a role in the future or might be useful in this context in the future.
I actually have a relevant question to Alex. Can we put an integrated geodetic reference station near the coast?
Yeah, technically you can. It's all about how long you want to keep it. So if you have stormy coasts, it might not be a good place to put it. The heart of the integrated geodetic reference station is really the foundation. That's something to be taken into account depending on the location. So yeah, it might be a very costly solution, but yeah, it can be placed there.
So we can combine the techniques, one single station for all.
Great question. Thank you. Thank you, Richa. So any one of you wants to comment on the question that I posed before that?
Yeah. I think what we were discussing in our group is that not many people have provided dynamic digital elevation models. So when we think about integrating various techniques, it would be really useful to have an elevation product as a function of time. And with such products over broad spatial scales, many applications will benefit from it because we can do projections based on such products. So I think that would be something to be looked in the future. We call it DDAM, so Dynamic Digital Elevation Models.
Thank you for that. Any last add-ons that you may have?
Okay, from an application perspective, right? Sure. For us, it's the same thing that I said in the last slide. Actually, it's a curated set of continuously updated data points that is most relevant for modeling purposes, because we don't need the surfaces. The DM, the topographical surface that you saw I can generate 5. If you use standard software, you can generate 15 types of surfaces from the points. The key problem is you actually want to know which is the one that the water path will actually follow in the context of the most pressing item of sea level rise and the surrounding implications around it.
Thank you so much for that. Okay, with that we have come to the end of this session. We heard various things, infrastructure, monitoring, the importance of integration, challenges and some solutions. Hopefully they are helpful for you. I hope it has been a great and insightful one for all of you. If you wish to know more about what we do in Singapore, please do come and have a chat with us. We are happy to discuss things further. And with that, I would like to give it back to our MC. Thank you so much.
Ladies and gentlemen, please join me in applauding our remarkable speakers and moderator. On behalf of everyone, I would like to extend our heartfelt thanks to Mr. Mulder for guiding us through this session and ensuring fruitful discussion. And for all speakers and moderator, please come forward. And I would like to invite once again Mr. Anton Wijanarto to deliver the token of appreciation. Okay, and let's have a photo session together. In 1, 2, and 3. Once again, in 1, 2, and 3. Thank you. Thank you all. Okay, ladies and gentlemen, now we have arrived at the closing of the second day of UN-GGCE International Workshop on the integration of terrestrial, maritime, build, and cadastral domains. Please join me in applauding ourselves. Before we end the event, I have some information for you. We need you to gather at the hotel lobby at 8:30 a.m. for tomorrow's technical visit. So please gather at 8:30 a.m. at the hotel lobby. The participants will be divided into 3 groups, with each group assigned to a different bus. You are encouraged to wear the t-shirt and the cap that were distributed on the first day, and for your convenience, wearing sneakers would be a great option. The committee will only provide basic medication, so please ensure you bring any personal medication you may need. Tomorrow, we will be visiting 3 locations, including the BIG office, Old Town of Jakarta, and the Mangrove Ecotourism Center. I think that's all. Ladies and gentlemen, on behalf of the organizing committee, I sincerely thank you for your enthusiasm and dedication. We also extend our apologies for any inconvenience experienced during the organization of this meeting. I am Tika, wishing you all safe and healthy, and thank you for being a part of this event. See you tomorrow. Wassalamualaikum warahmatullahi wabarakatuh.